realm of superficiality and take the big picture in. Becket, you've been in contact with members of the Comet Research Group. I would really like to get caught up to speed on that. We could launch in like that, and you start telling me about it, and then you can tell me about Alan West, and I can talk to you about how much I respect Alan West and the work he's doing, and then he's going to be at the Cosmic Summit, and then we could talk about that.
Yeah, and I think how we can kind of start it off is be like, okay, well, over the last 2 episodes, we've been looking at how Ice Age floods are not just geological events, that they could be the gateway to us rethinking our entire civilization, which is kind of where we're going today with these comet impacts, cosmic impact events, or we could say cataclysmic events. And the Comet Research Group is kind of the leading... I guess they are.
Well, they are. They are now. I would say they're the tip of the spear when it comes to doing major impact research right now as a coherent group rather than just isolated. A lot of people are doing research on impacts, but that organization is, I think, definitely laying down the most relevant and important information in our ongoing. Increasing knowledge of impact events, primarily because what they're doing brings it home, puts it right in our lap.
Right.
Rather than being something very interesting, profoundly interesting within the history of life and in the geological history of the Earth and all of that, right? But it doesn't have that same direct bearing and immediacy onto the human level like the work of the Comet Research Group. Because what this does is it opens those windows of heaven to this whole possibility that major impact events have occurred during the time, the reign, if you will, of our species, Homo sapiens sapiens. However long we go back, maybe a couple of 100,000 years, maybe. It's sure starting to look like it. But so if that's true, what that means is that in a couple of 100,000 years, our ancestors from time to time underwent multiple events. Because even if you set a timetable of every 10 or 20,000 years, well, boom, even if you make it every 20,000, and we certainly have enough data in hand to think that the periodicity of impact events on a scale that could be major effects on civilization or on human species, humans and other species. Well, if those happen every 20,000 years, well, you can see we've got 10 of them in the time that our
humans have been around. Yeah,
humans have been around, and it's 20,000 years now. The Younger Dryas event appears to have been the most severe. Seems to have been the most recent major event like that occurred on a global scale. However, all we have to do, we can look at the ice cores, we can look at sea level cores, we can look at tree rings, we can blah, 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 blah. We can go down the list of proxies that we can look at. They're all pointing to the fact that, there have been multiple times when the normal, nice, sedate, placid background change has been the order of the day, when that suddenly gets interrupted. And the whole realm of nature is just convulsed for a short period of time. And when the convulsions are over, there's a whole new regime that's settled into place.
Yeah, and the Comet Research Group has kind of been the group that's been looking at places all over the world. So we've focused a lot of our last 2 podcasts directly on the northwestern United States and Bonneville, Missoula flood regions. What other areas around the world are we going to explore for evidence of a cataclysmic event?
Oh, we've got plenty of places, and what's emerging from this is we've kind of we essentially we're connecting the dots here. We put a fairly dense cluster of dots up in the Pacific Northwest over the last 2 episodes. What I'd like to do now is put some more dots in other places around the country, let me say the continent, particularly of North America. And I think there's enough evidence accumulating there now that, yeah, we can conclude pretty confidently that North America was ground zero in the Younger Dryas. We can conclude that. I mean, I think that's pretty overwhelmingly clear. And we can talk about why. But in order to understand why, it's necessary to look at a more detailed picture of the events. So we haven't looked, for example, in the Southwest. We haven't looked in the Southeast. We haven't really looked in the Northeast. So I thought we should go some of these areas up into Canada and let the denizens of North America know that no matter where you live, the imprints, the evidence of these cosmic convulsions are all around you. They're in your backyard. You might be living right on top of them and not even know it. Yeah. And if you go to work and you're in a building made out of concrete, yeah, that concrete is pretty much the byproduct of reassembling the leftovers of the last or previous several global catastrophes. Because what's what goes into the primary ingredients of concrete is what? Gravel. Well, the lime and the gravel, yeah, the cement. Okay, particularly the gravel. I've been to probably 50 gravel pits on my travels around, right? And you learn a lot from a gravel pit. But one of the things that is consistent about pretty much all of the gravel pits is they're all byproducts of enormous extreme upheavals and catastrophes. Because what's the primary byproduct of a flood? Well, you get sediments. Floods you'll have the background flow, which is, in a normal river, normal creek. It might be vigorous, but it's not catastrophic, obviously. And if you go to any creek or river and you walk along the banks of the creek or river and you look at the channel and you look at the channel geometry, it's not going to change much from year to year to year. But then you might get a 100-year event. Let's say you get a heavy rainstorm and you get a 50 or 100-year event. Well, now you go back and you're going to notice that there have been more changes made within 2 or 3 days than probably 20 years.
And that kind of happened in Western North Carolina recently.
Would
that be an example?
That would definitely be an example. That's exactly what happened. And there was more geomorphic. To find an equivalent level of geomorphic work done on that region of North Carolina, I believe we have to go back to, I'm pretty sure 1916. And in 1916, there was an anomalous extreme weather event. Yeah, I think that's the year. Asheville flood, 1916. See if I'm pulling this out of my memory from...
The Great Flood of 1916 in Asheville, North Carolina was a devastating event caused by 2 back-to-back hurricanes that dumped torrential rain, leading to widespread destruction and the loss of at least 80 lives.
Yeah, so that's what I'm referring to. So that was of an equivalent severity to what happened. I mean, so...
And there's your 100-year cycle right there.
There's your 100-year cycle right there, yeah. So, the knee-jerk reaction to something like this among certain political factions is to blame this on, climate change, which has been redefined to exclude everything except for anthropogenic climate change. That's how the narrative has been contrived in order to redefine the terms. If you'd have said climate change 25 years ago, you could be talking about a whole spectrum of things, and anybody who was in a conversation or reading a paper or whatever that said climate change, they wouldn't just be thinking carbon dioxide and greenhouse warming, right? They wouldn't be thinking that global warming. You'd have to be thinking about a bunch of things, right? You might be thinking about ocean currents. You might be thinking about, changing. You might be thinking about volcanic eruptions, which can produce effects that can last for years. You might be looking at changes in solar radiation, which was always considered to be a possibility up until the 1990s. And then what happened? Well, solar science kind of got sidelined, right, because the focus was on carbon dioxide. So the solar physicists and solar scientists are busy studying and learning a lot about the sun and realizing that the sun is a whole lot more dynamic than anybody had assumed, a decade or two or three earlier. Although there were those who always were speculating and seemed to draw a direct connection between what the sun was doing up there and what was happening in the world down here below in terms of climate change. But all that got excluded, see, with the politicization of the climate science, the climate change science, it all became directed towards anthropogenic, because anthropogenic is going to give partisan factions control, whether it's social control, political control, or economic control. Because if you look at all the policies that are being proposed to combat carbon dioxide-driven global warming, they all have enormous economic consequences, and they favor a few. You definitely can see, there are favored groups within that, and the reallocation of money and resources towards addressing what I consider to be a completely overblown narrative, that of greenhouse global warming.
Right, and so you mentioned you mentioned activity with the sun, you mentioned volcanic eruptions. They do impact the climate. So what
absolutely.
you're saying is that anthropogenic effects on the climate are what's been overblown, not that the climate doesn't change.
Of course not. No, and I'm of course not saying that humans don't have an effect on the climate, because good Lord, we do.
It's just overblown.
It's just overblown. Right, it is. The role of carbon dioxide in the whole warming scenario is overblown.
So why do you think carbon dioxide is the thing that they're tracking? Obviously, people have economic incentive by this, but is there a reason they chose carbon dioxide levels?
Oh, well, yeah, it's totally not arbitrary. It's because, carbon dioxide is the fundamental molecule of the whole process. There's talk about, methane and talk about nitrogen, but carbon dioxide is the primary known greenhouse gas. So you're starting from a well-known premise that carbon dioxide is a quote, unquote, greenhouse gas. In other words, it captures longer wavelengths and re-radiates it to the earth, right? It has this sort of insulation, or you almost think of it as a canopy, because the fast-moving radiation comes in and it's transparent. The atmosphere is transparent. It comes in, it is absorbed into the solid mass of the earth and is re-radiated at a different wavelength that to which it is not transparent to carbon dioxide. So carbon dioxide then catches some of that and re-radiates it back to the earth. But there's a point at which that process ceases to function in any meaningful respect. And that's pretty much where we're at now. And you would have to dump 10,000 parts per million into the atmosphere, really, and of course, like anything, if it's out of balance, there's going to be negative consequences. But carbon dioxide, at 406, 410 parts per million that it is right now, is still at some of the lowest it's been in the whole Phanerozoic, or eon of visible life, which is what that means. The Phanerozoic, phanes means light, zoic means life. So light and life together give you Phanerozoic. So we talk about the Phanerozoic, which is the great period of time, Earth history, that engulfs life. That started with the most primitive microbial life on one end and ended up with us on the other end. You and me sitting here having this conversation.
That's a strange period of time, isn't it?
Yeah. And then not to exclude, 7 or 8 billion other people.
Yeah, those two, right?
Well, yeah. So I didn't mean to ramble there, but...
no, it's interesting. I had questions for you about that, and sometimes I read the comments on this, and it seems like people don't think that you believe that the climate changes, or maybe that term is just not really fair to use. It's a gotcha term.
I think what we want to do is redefine that term.
Let's do it.
And because it is completely ridiculous to say that I'm, well, he's a climate change denier. And it was getting called that prompted me to write a very long essay of 30 or 40 pages entitled, Who Are the Real Deniers? Well, the real deniers is not me, because, look, is there anywhere that you see me, I'll challenge anybody, find somewhere where I'm denying that the climate changes. I mean, now there is one recording of me. I'm outside. It's been a few years now, but I'm outside and I'm looking up at the sky and I'm waving my fist and I'm shouting out, I deny that you exist. I deny that climate changes. I did.
Oh, no.
So
obviously we can't take anything you say moving forward seriously.
That's right, because it didn't matter with what force or projection, it didn't stop changing.
Yeah.
It just continued changing right on, so.
You must have been wildly wrong then.
Apparently so.
What are we going to do?
Yeah. So anyways, yes, let's give that lie the rest that it deserves. I do not deny the climate changes at all. In fact, what I keep preaching about and talking about and ranting about is how much the climate changes, and that we have to get the big picture of climate change and not just focus on one variable in a very complex equation.
Right, and we looked at this every single time we've talked about impact events, too. You've shown the chart of how much the climate changes. And
yeah.
when you look at this small little window of the last 1,000 years, it's very difficult to get the big picture of just how much the climate has changed.
Yeah, well.
Okay, so last time, just to kind of pick up where we left off from last episode and where we're going with this climate change, cosmic impact conversation. Last time we kind of left off at finishing looking at the Bonneville and Missoula floods and showing what had happened in the Northwest United States and in North America. Are we exploring different parts of America today?
Yes, I think you are. And you're going to be surprised at some of the things that we look at. But I want to say that if there's a takeaway from what we've done so far, it's we addressed, I think we did, even a couple of episodes to the Missoula floods, and we did one episode to the Bonneville flood, right? What the takeaway is, I want people to, it was like that focus on, remember Tammany Bar?
Mm-hmm. Yes.
Tammany Bar along the Snake River. It's just north of the mouth of Hell's Canyon. So the last major significant flow or story of that Bonneville flood was its passage and undoubtedly its deepening of Hell's Canyon, which is deeper actually than the Grand Canyon in places, right? So once it got out of there, it you can see that it opens up considerably in the basin that Lewiston and Clarkston are. It actually is like in a bowl, right? And so once those floodwaters of the Bonneville flood have come through and enlarged and downcut, eroded Hell's Canyon, which was undoubtedly already there, but what would have happened is it would have been enlarged by 40 million cubic feet per second passing through there for maybe up to a year perhaps, but probably closer to somewhere between 3 and 6 months. Because remember, you had this huge inland sea almost of a lake in the Bonneville Basin in Utah, where Great Salt Lake is now. And we saw evidence that you had this huge body of water, almost 1,000 feet deep. Remember, it dropped by 350 feet or so when it burst through that northern passageway. Now, how long did it take for that entire 350 feet? Well, I've seen various estimates, and it all comes down to, how fast was the water moving out? If it was moving out at a slower rate than a faster rate, it's going to take longer. But the range was somewhere, I think, initially maybe a year, and then they realized that the flow rates were greater, which actually would have implied that it was more catastrophic than they thought. And so now the total duration of the lake emptying was, I think, estimated between 3 and 6 months. But here's the thing we want to remember, and then we'll move on to the next part of this investigation, is that at Tammany Bar, that's where the Great Missoula Flood met the Bonneville Flood.
Right.
And sorting out that relation between those two enormous hydraulic events, some of the most stupendous, epic hydraulic events in North America. Now, Missoula, remember, was actually 1 order of magnitude greater than Bonneville. But the Bonneville was still a very impressive flood, and it was focused. It tended to be more focused along a narrower area than the Missoula flood.
Right.
So it still did an enormous amount of very impressive geomorphic work in its passage. And in fact, that's what we're going to go in May. We're going to go, and we're going to actually, with Brad, Brad Young, we're going to start in Lake Bonneville, there by Salt Lake, and we're going to head north, and we're going to go through Red Rock Pass, which was the outburst point. We're going to see where these waters poured through this aperture in the mountains, and then we're going to follow that north. It'll cut to the west, and we'll see where it emerged out onto the Snake River Plain. Then we'll follow the evidence from Pocatello, where it discharges out onto the Snake River Plain, all the way to the southern mouth of Hell's Canyon. And we'll follow that whole route, looking at the evidence and the different kinds of evidence in the landscape and so by the time we get to the end of it, anybody who participates in it is going to have a pretty good idea of a cross section.
What we've just talked about over the last 2 episodes.
Right. And it's like, you know what it's like? Here's an analogy I like to, if you go spend 2 weeks in France, I know, like when I did, I came away, with I could carry on a very rudimentary conversation. I come away with some French vocabulary, right? If I see, I'm meeting some lady and she, has a young one there, I would say, quel enfant charmant.
Ooh, don't do it to the ladies, Randall. Don't start speaking French now.
But most of my French I forgot. But here's what I'm getting at. Okay, you go hang out somewhere people are talking and you listen and you try to learn. Yeah, you're going to soon start picking up the vocabulary. That's what this is like.
Are you, just to be clear, are you comparing yourself to a beautiful French woman?
No, I'm comparing myself to a suave, debonair French playboy.
Okay, there we are.
That's more fitting, isn't it?
I guess. Well, hopefully people learn as much as they would by paying attention to the suave, debonair French gentleman.
Yeah, well, because I am so I'm half Swedish, right? But the next most predominant ethnic nationality is French. Yeah, my mother's their whole line of the family was the Petits, the immigrants from France.
Oh, okay.
Yes.
Good to know.
My mother's mother was a Petit, and a lot of the French settled in Louisiana. You might have known that.
So your background is at least partly French, Swedish, French?
Yeah, I would say Swedish is the big one and French is the next one. And then a mix of some Welsh. There's some Welsh in there, some Cherokee Indian, because we have 2 lines of the family, the Durdens and the Petits, when they came to Georgia, both intermarried with the Cherokee. And I forget the exact, but I mean, it's back there. It's so small, like maybe a 32nd. I don't think it's more than a 32nd. But they actually show up in our family tree. I got an aunt that did the whole thing on that side of the family. And we had a family reunion, this was 25 years ago, and I could see at least my mother's side of the family.
Yeah.
Father, I don't know, but one thing I don't really know any of my, beyond my my grandfather, who was an immigrant from Sweden. He came over from Sweden in about 1910, and he was 15 or 16 years old, and then he never went back. But I have an uncle, not an uncle, a cousin, second cousin. He was my dad's cousin, right? Okay, so my dad's cousin went back to Sweden, where my grandfather came from, and he found out that my grandfather had a nephew. I think that was what it was, a nephew over in Sweden. And the nephew was the same age as my dad. And so I guess him and my dad would have been like, I don't know, second cousins, third cousins. Somehow I forget the exact geometry of it. But he said, well, I met your cousin over there. I think they were cousins maybe. Anyways, I met your cousin over there, because he was the same age as my dad. And he had 3 sons. And the 3 sons were all the same ages as me and my 2 brothers, which was weird.
What are the odds of that?
I know. That's what I wondered. What are the odds of that? I have no idea, but he said it was pretty weird.
There's a mirror picture of the Carlson family living in Sweden.
Yeah. So somewhere I've got like these second or third cousins over there. There's this family with the dad, same age as my dad, and he's got 3 sons. So, yeah, and they're the same age as myself and my 2 younger brothers. Anyways, that's
very interesting. Very interesting.
It is interesting, and an interesting little sidelight. And I will say that, my grandfather coming over, that was post-glacial meltdown because, Sweden was completely covered in glaciers, in ice, during the late, it was called the Washelian. It's the counterpart to the Wisconsin. But during the Washelian in Europe, northwestern Europe, all of Scandinavia was buried.
When was that? How long ago?
Well, that was same period of time.
Okay.
And its catastrophic destruction and melting was occurring apparently at the same time as the ice complex over North America. Yeah, which is interesting. And I'm not prepared to go there yet, but we need to look because there's a lot of new information that's come out. Plus, a lot of information since the end of the Cold War, and of course all of that got subverted with all this stupid geopolitics that these idiots that are in charge are stirring up. But once the Cold War ended and the Soviet Union ended up, there began a lot more scientific exchange between the U.S. and Russia. And one of the outcomes of that is the geology started getting access to a lot more of the geological studies from Russia. And that's a big chunk of the Earth's surface, right?
Oh, yeah.
Well, what do we start seeing there? Same thing. Altai Mountains. There's a whole region up there that was subjected to flows, catastrophic flows on the same scale as the Missoula floods.
Wow.
We're talking 700, 800 million cubic feet per second. Yeah. So.
And that's dated around the same time.
Well, apparently, but I've recently gathered a lot of the available information, and I've archived it, and I've not yet gone through it. But the preliminary examination of this and the dating suggests that, yeah, it was commensurate with the melting in North America.
Wow, that would have been a bad period of time to be around.
Yes, it would have. People want to look it up. It's called the Altai Flood, Altai, Altai Flood. But maybe even in the next episode we'll talk about that we record. That'll give me a little time to put together a presentation. I've got some images and some graphics and maps and things that would, of course, be very helpful in getting the picture. But I think that the thing to understand is that, yeah, what's happening is we're discovering that this story, if you will, is definitely planetary in its scale, and it's left imprints that once you know how to read them, to decipher them, are embedded in the whole planet in various ways. Some places subtle, some places extreme. But we're at a position now where we can actually begin to read this stuff because, 50 years ago, we didn't have LIDAR, we didn't have ground-penetrating radar, we didn't have digital elevation maps and models like we have now. We didn't have the data of tree ring climate changes. We didn't have the ice cores like we have now that have been analyzed. We didn't have the seafloor cores. It goes on and on.
Yeah. Well, I have to ask, Randall, because you're talking about the technology that we have recently. Did you see what has kind of happened? I would be very surprised if you haven't seen the scans, the new scanning technology that they used for the pyramids. I'm sure people want to hear what your perspective is on the supposed underground structures and tunnels that...
Well, I'm going to record something next week where I talk about it more in depth, but for now, I don't want to get too sidelined from what I actually had prepared, but good question. Basically, what we can show in terms of, global changes and megafloods is we can show that pretty much every place on Earth has at one time or another been subject to extreme pluvial events. And that includes North Africa. It includes Egypt. And, that became apparent back in the 1980s with the shuttle radar that first was able to peer through the sand sheet there in the Sahara Desert. And what they were able to see under the sand was a whole network of erosional features that had been carved by running water. So it's become very apparent since the late 1980s. I think this first shuttle overflight that imaged this was in, I think it was 1988. I could actually pull it up on break, except I am going to do a more
comprehensive.
More comprehensive. Okay, then we also have like the Nile Valley, the Nile Canyon, we'll refer to it, because the valley, when you think of the Nile and you talk about the Nile Valley, you're looking at this nice, fairly level layer of alluvium that all the agriculture of Egypt is being undertaken in the Nile Valley on these nice flood terraces, and the whole history of Egypt and why it was able to emerge from the barbarian backdrop in that particular area was because of the fertility of the Nile Valley and the fresh soil, topsoil that was deposited during these Nile River floods that came every year, almost like clockwork, but maybe with some important disruptions to that process, as a matter of fact. But for the most part, coming like clockwork. And the clock that was used to time it coincidentally was this relationship, this correspondence between what's happening here below on the planetary surface with the annual flooding of the Nile, because that was that was a result of the monsoon rains over the southern highlands in the headwaters of both the Blue and the White Nile. So those rains would come in, and then you'd have that flow north now. You picture the Nile, it's flowing north.
Good to put that conspiracy to rest.
That the direction of the Nile River was mysteriously reversed last night.
Hey, do you guys know that if you go and look at what AI says, it says the Nile River flows from north to south.
Somebody needs to retrain that AI.
Somebody needs to retrain that. Now it's going to hear this, and somebody's going to look, and it's going to be fixed by the time.
South to north. It flows south to north. It flows into the Mediterranean. Yep. It starts in the Ethiopian highlands, flows north. Now, here's the thing I wanted to get at, back to the question you asked. So you got this nice verdant valley, lush. The river comes through. Even during the flood, it's somewhat vigorous, but it's still, a pleasant, well-domiciled river, right? Well, the thing of it is that if you're standing there next to the actual river, you're standing on top of a column of alluvium that includes both material washed down from the highlands, but also marine material that's been backwashed up from the Mediterranean, right? If you were to now scoop out the infill, the sedimentary infill, you'd be looking at a canyon 6,000, 7,000, in some places even 8,000 feet deep. It's a gigantic deep gash in the earth. but it has also served as a repository for the infill of all of this material that has been washed into it. And the material that's been washed into it is material that's been carried, stripped from the uplands, stripped from the ground above, carried in floodwaters. That floodwater has become channelized and most likely repeated catastrophic floods, downcut that slot, right, that discharges into the eastern Mediterranean. Well, this process began when, for whatever reason and however we explain it, the waters of the Mediterranean dried up. The whole Mediterranean disappeared, I think between 5 and 7 million years ago. Mm. And at some point, the Atlantic Ocean, which was barricaded, and I haven't studied the most recent research on this, the Zanclean flood was when the dam, if you will, at the Straits of Gibraltar burst, and the waters of the Atlantic poured in and filled the Mediterranean basin. But when it was dry, if you were down on that floor, which I think was like a mile lower than the ocean surface now, and you were standing where the Nile Delta is, right, and you were looking south, you would have been looking at basically a canyon that was as deep as the Grand Canyon in front of you. And that is what's now filled with sediment, and that's the Nile Valley. And that sediment splays out from the Nile Valley and forms the delta. And then the delta transitions to below sea level, right? But that whole delta is now being used for agriculture and so on, and was inhabited in Neolithic times. But see, so here's the point. There's been enough erosion of that limestone, and it's mostly limestone. The Giza Plateau is mostly limestone, Eocene limestone, thick limestone. The point is that we have evidence, growing evidence, that there have been enormous flows of water over the surface of what is now the Sahara Desert, including Libya and Western Egypt, right? Some of that water undoubtedly discharged through the Nile. Some of it probably discharged straight north into the Mediterranean basin by various routes, right? And we have evidence of enormous amounts of erosion. Now, that channel that I just described and talked about, I mean, that's just within, a few hundred yards of the edge of the plateau there where the pyramids are. Mm-hmm. So here's what I'm getting at, is that it would be perfectly believable that there could be caverns, cavities, caves, some of them pretty large, honeycomb through the limestone bedrock under the pyramids. Now, at this point, I would not be willing to go any further than that.
Yeah. I mean, I think it's worth it to show the actual scan, because most people who are talking about this have just seen like this 3D artistic depiction of what this scan could be. And this is Johanna James' post. Yeah. Shout out to Johanna.
It is I look at that and I go, okay, what actually is this showing? And I'm not prepared to go from the image on the left to the image on the right.
No, it's a jump.
It's a huge jump. Now, there is examples of very large shaft-like caves. Let's see, there's one right there along the coast of Libya to the, let's see, I can tell you what it is here. Let's see here.
So further investigation is needed, and you're going to be making a more comprehensive video about this for people.
Yeah, I mean, I wanted to talk in more detail about the Zanclean event and the, and the erosion and what might that have to, how that might be related to the controversy about the age of the Sphinx, because clearly, the controversy with the Sphinx was, well, does the Sphinx have evidence of major water erosion? Well, if it does, then you have to go, okay, when was there enough water available to erode to create that level of erosion? And, when I went there, what I saw was that they've been doing so many reconstruction campaigns, restoration campaigns on the Sphinx, that it's hard to determine what was the original. If they had not done any restoration campaigns in the recent centuries, or even in older times, what would we be seeing? Because you look at it, and a lot of what you're seeing is restored masonry. So I think perhaps kind of misleading, but if you look at the walls of the ditch around it, nobody's tried to restore that. And to me, that's now almost more valuable than the Sphinx itself. Because clearly, I think it has, in every way, it's consistent with water erosion. And that's my opinion on that. And I know there's others who have other opinions, such as, groundwater sapping and things like that. But I think there's enough evidence to suggest that it was a surface flow, that it was an overwash, that it was a sheet wash moving over the thing. It was probably coming from the west, because that goes up in elevation, and that would be consistent with the fact that there are channels incised into the bedrock under the sand sheet. That was the whole importance and value of the shuttle overflights, is because for the first time we were able to peer beneath the sand and see that the bedrock under the sand is all completely channeled, paleo-channeled, you would call it, with evidence of overland sheet floods washing over what is now pretty much the Sahara Desert, which I think would have to be attributable to pluvial events. And that's what they're calling them, like pluvial period, which means rainfall. Question is to now refine that. You could say, okay, there was a broad span of 3,000 years or 5,000 years where rainfall was more plentiful than now. And that's absolutely the case, because we can see the evidence of when the Sahara was basically green and occupied and had lakes. So obviously that was a very different climatic regime. So I find it really rather ironic that one could be talking about such things on that scale, climate changing on that scale, and yet have someone accuse you of being a climate change denier. I just find that very interesting. Did you find? I wish I could remember the name of that cave, because I want to put it. It's a good example.
You said in Libya?
It's in Libya, right along the north coast. It's actually one of the deepest caves in the world, or biggest caves in the world. That might be the one I'm thinking of. Yeah. Well, there are caves, very large caves, that actually exist. So I guess the point I'm getting at here is that, yeah, all the pieces fit for, enough erosion taking place over this terrain that there could be large cavities and caves, but the question is that what this synthetic aperture radar is showing? I don't know what that is.
Yeah.
It sure looks, go pull that back up again and look, and you'll look at the central one there looks like it has the most coherent organization to it.
Yeah.
That one right there, yeah. Well, I want to see more evidence. I want to see some peer review. I want to see some independent corroboration. I just want to see more studies, because I look at that and I go, yeah, well, what the hell is that? Is it natural?
That's a great question, isn't it? That's the question we should be asking.
Yeah.
What the hell is
now,
that?
If it wasn't maybe it's something that could have been natural and then got modified, because we see many examples of that. You start out with a cave and you enlarge it, you resculpt it into so it could very well be natural cavities that were then modified.
Mm-hmm.
But then you have to get access to that. I mean, and certainly caves, you could be looking at going down thousands of feet. So if you had natural caves, now could it be that there are connections, there are entrances to those caves, but they're within or under the pyramids? Sure. I mean, now that's not so,
implausible?
No, it's not implausible. And what, Andrew Collins, he wrote a book about that.
Yeah.
I haven't read it yet, but now I want to check it. So he might have been kind of ahead of the game on this. Yeah, Andrew B. Collins, there we go.
He's with Shock and Armando.
Uh-huh. So he was proposing that there were caves under the Giza Plateau. But that's something I've thought for a long time. I mean, when I first learned about reading about the article, it was on the Selima sand sheet. Pull up Selima, Selima sand sheet. Mapping. Yeah, paleohydrography. Look at that, paleohydrography in deserts. Space-borne imaging radar. That's your SRI.
Here's the abstract of a paper.
Paleo drainage. There we go. In the Selima sand sheet were determined using high-resolution multi-wavelength multipolarization space-borne imaging radar data. And the global land one-kin base elevation, project digital elevation, okay? Yeah, okay, there we go. The combined use of these two data sets shows that both large flood features and later superimposed drainage channels of variable morphology all drain northeast and east-northeast from northwest Sudan toward the Kharga Depression in southern Egypt. Okay, this is actually not the particular study I was referring to, but it's the same thing. It's just showing, again, that hidden beneath the surface is this whole landscape showing a completely different, let's see. Yeah, these directions are opposite to those of the Trans-African drainage system model, in which the large flood features are considered to flow southwest across northeastern Africa into the Chad Basin. Internal drainage operated in the general.
Okay, so when I hear that they're opposite in direction of that, it makes me think that there is some type of, and this could just be my ignorance, but it makes me think that there's some type of massive force of water going the opposite direction than what we see today.
Yeah, it's one you could look at that way. In fact, my first impression would be is once we're understanding the magnitude and how dynamic these paleohydraulic events are, we have to begin to realize, oh my God, we're looking at sometimes where you can have maybe a cataclysmic flow in one direction followed by a cataclysmic flow in a completely different direction. But how do you explain that? Well, I mean, in terms of tsunami deposits, it's obvious to explain because you have the run up on the land, and then you have the backwash into the ocean. So you've got up and reverse, right? So anywhere where you would have something like, say, a basin that filled with water and then empties, you're going to get a bidirectional flow. And I don't know, I haven't studied enough on Africa, other than to know that Africa has an interesting sort of subsurface geomorphology or topography, in that it's a series of basins surrounded by highland areas. So you could have a lot of rain filling one basin, and it could overflow into another one. And perhaps that could reverse. I wasn't intending to talk about that. I will show that in the presentation I'm going to do next week. I'll show that because the takeaway from this, again, relative to the question, is that we know that there have been large-scale pluvial events and fluvial. Fluvial meaning flowing water, pluvial meaning rainfall. And, of course, obviously they're related to each other. If you have a heavy rainfall, pluvial, you're going to also have a heavy fluvial consequence of it, right? So the argument could be made that particularly limestone bedrock terrains could be honeycombed with caves. Now, to what extent were those caves accessed by humans? that's an open question, and I don't think anybody, to my knowledge, has really proposed, anything beyond the typical caveman scenario. Nobody's assuming that maybe people are going into caves hundreds of yards underground, and maybe there are large areas that could have been inhabited, but that seems entirely feasible. And so, again, I don't know what we're looking at there. That one central column in particular looks like too organized to be natural. But I don't know. We're going to wait and see.
Yeah, we will. Well, thanks for diving into that too. I was very curious what your perspective was thus far. So where are we picking up? Where are we picking up in North America?
Okay, so what I'm going to do here is I'm going to open Google Maps to start, and we're going to go up to British Columbia.
Have you ever been to British Columbia?
Oh, yeah, multiple times to research what I'm about to show you.
When was the last time you went?
Oh, God. 10, 12 years ago, I guess. Yeah, 10, 12 years ago. Somewhere, I'm going to guess, because I think the last time I was there, I visited the studio of the Grimerica boys,
Yeah.
Darren Grimes and Graham Dunlap. And we did a podcast together. And Bradley Young was there, and several other people were all gathered around and crammed into their studio, which I think they've upgraded since then. But that was the last time, so I'm guessing that was 10 years ago now,
Wow.
maybe. And I think that was my third time up there.
I guess while you're pulling that up, we could do a little plug for the Bonneville flood. Bonneville flood tour that you're doing. You started talking about it earlier, but that's in May 11th, something.
May
like that?
11th, and yeah, we're going to
Yeah.
be following the route of the Great Bonneville Flood.
Right.
And seeing what happens to landscapes when 40 million cubic feet per second flows over those landscapes for a period of 3 or 4 or 5 months, and what it does in the aftermath. And so it's going to be not just looking at some amazing landscapes, but it's also going to be learning to read this script, if you want to call it that, this epic tale of which the Bonneville Flood is a part.
Right. Being able to speak a little bit of flood French, as you
There
might
we
say.
go. Yes. There we go. I like that.
Awesome. Well, there's a couple spots left, I presume.
There's a few, I think the last I heard there was 6, but that was a while ago, so I don't think it's sold out. I think there's 3 or 4 spots left,
Okay.
if I had to guess.
So 3 or 4 spots left. If you guys want to see what we're talking about, get them. Snatch
Oh,
up
yeah,
the
check it
tickets.
out. We're going to have so if you go to randallcarlson.com and put in Bonneville Flood May, I think we've got some more information on it. But if you're interested at all in understanding the big picture of Earth change, and this is a very good way to introduce yourself into that realm of knowledge. And one of the consistent reports, feedbacks that I get from people that have attended these tours is that they really begin, there we go. Join Randall, Carlson, Brad, and the Grimerica team for an unforgettable 6-day adventure as we trace the path of the ancient Bonneville Flood through Utah and Idaho. This immersive geological tour offers a rare opportunity to witness the remnants of one of North America's most significant cataclysmic events, the massive flood that reshaped the landscape as Lake Bonneville burst its natural dam thousands of years ago. Guided by Randall's deep knowledge of Earth's catastrophic history, this trip will take you to iconic locations showcasing the incredible forces that carved out the landscape. Each day will feature hikes, geological discussions, and moments of awe as we delve into the story behind the terrain. I couldn't have said it better myself. Did
you
I say
tickets.
that? I don't know who wrote that. I don't think I did, but that was really well. Who wrote that? Was that Darren? That's really what was it? Brad?
Who knows?
It was well written.
It was well written. It was. It was very. We're going to use that audio for an ad. We didn't even have to script it. It was already done for us.
Hot dog, hallelujah.
There we go.
Okay, let me get my map over on this monitor. Yeah, Canada indicates detachment of the Laurentide ice sheet from the Rocky Mountains at approximately 15,000 years ago. I would suggest that it's probably closer to 14,006, which would make it more consistent with Meltwater Pulse 1A, but it's certainly within that window. Because Meltwater Pulse 1, what do you got there? I saw 14.9. There it is. Let's see. Based on a group of 12 samples well clustered in time, we date the detachment of the western Laurentide ice sheet margin from the Rocky Mountain front to approximately 14.9 plus or minus 0.9 thousand years ago. This is 1,000 years later than previously assumed. Yes, and I think that could still be 1,000 years, maybe not, maybe 300, 400 years. Because I said 14.6 is, I think, the latest date for Meltwater Pulse 1A. And my first impression would be that this is probably going to be a regional manifestation of whatever triggered that melting event at 14.6.
Mm-hmm.
So let's see. A later separation of the western Laurentide ice sheet margin from the mountain front implies higher ice margin retreat rates in order to meet the younger, driest ice margin position. Well, we knew that. Yes, it implies higher ice margin retreat rates. This is the whole direction and that this research is moving, is that these things are happening a lot faster than people were imagining a few decades ago. And we're having to rethink some of the temporal models for these events. And I think what we're going to do, like here, so I'm saying 14.6, this is 14.9.
Yeah.
So you're only, 300 years off?
Just about.
And yeah, I want to read this study here. Okay, so this introduces, let's go. Do you have images?
Yeah.
Let's see, go to images. Yeah.
What do we want to look at here?
Let's see here. Okay, I've got the foothill glacial. Okay, that second from the left, that shows the map. You can get the picture there. Okay, so you see right there the origin. You see this right here. This the boundary between British Columbia and Alberta forms the continental divide of the western North American continent. Right? That's the divide right there. So you can see that this thing, the erratic's train originates right there on the continental divide, and then it follows this route down. It goes by Calgary right in here, loops to the east, and then finally comes to an end in Montana. So what is it exactly?
Yeah, what is the erratic's train?
Okay, well, okay, scroll down and you will see second from the left. You're hovering almost right there. Yeah, open that. Okay, so as you would guess from a train, it's something on the order of 500 miles from its source there on the British Columbia-Alberta border where we saw to its final example there in Montana. And there's hundreds of them, but these are examples here. And they're all of the same type of rock. It's a type of metaquartzite. It's a metamorphic rock, similar to granite in a way, metaquartzite. So the question then is that what are we looking at here? We're looking at a string of these boulders, and you can see. Look at the top row, third from the left. You can see that's a pretty big rock there,
Yeah.
right? You see the guy standing next to it. You go to the next one at D, same thing there. That's a pretty good-sized rock.
Yeah.
And you can trace these things in this line that we just saw on the map over 500 miles.
Wow.
So if you were, this is to me, it's very much like forensic geology. Okay, we're looking at this and we're trying to go, okay, this rock didn't move itself here. So by what exact mechanism of transport can we attribute to the geographic disposition of these rocks? How do we do that?
I mean, we chalk it up to giants moving rocks, and we
Well,
call it a day.
there's that, but in a way, there is a certain element of truth to that. So this is the kind of thing that, I mean, who knows about this? Who thinks about it? Who has any concept, really, of what the significance of this would be? Well, not very many people, I can tell you that. And you're about, though, to become one of them. If you feel intrepid enough.
Mm-hmm. It is of interest to me to become one of them.
Become one. So this is the foothills erratic terrain. Okay, the foothills are the foothills of the Rocky Mountains.
Okay.
And you have this region called the Rocky Mountain Front. And anybody who's been to Denver and looks to the west sees the Rocky Mountain Front right there, splayed out, right? Well, it goes all the way up into Canada. And so you've got the, what I'll do here is I am going to share screen, and we're going to take a look here. Okay, so if we go to Calgary, right, so all of this is part of the Rocky Mountain Front. So check this out. All of this is the Rocky Mountain Front. And then you go east of the Rocky Mountain Front, now you're out onto the Great Prairie, the Mid-Continental Prairie. And, it's always so fascinating to me how, especially if you're coming from the east and you're traveling across the prairie, and the Rocky Mountain Front just looms up in front of you. It's such a dramatic change in landscapes. I never cease to be impressed when I make that run. Okay, so anyways, we can go up here, and we can see that this, right here by the little town of Hinton, we've got 16, and here we've got the Athabasca River. And there's since we were getting earlier talking about the French have a term that is often used for what's happening here with the river. You'll notice that it's flowing in this confined channel, right? Mm-hmm. And then it opens up. It moves out of and in front of the mountains and the confinement within the mountain canyons. And the French term is débouche. Débouche. The river debouches. Debouches? I guess that's it. It done debouches here from the river, from the mountains. No, it's a French term, debouche. How do you spell it?
Debouche.
Debouche.
D-E-B-O-U-C-H-E.
D-E-B-O-U-C-H-E is probably the spelling.
Probably right.
Are you looking it up?
Yeah, I'm Googling.
Okay, good. Let's get this settled once and for all. Debouche.
Debouching river. No E. D-E-B-O-U-C-H.
Oh, well, that's probably the Americanized way of spelling.
Yeah,
Okay,
exactly.
so what does it say? What's the definition?
In hydrology, a debouche, or debouche with an E on the end, is a place where runoff from a small confined space discharges into a larger, broader body of water.
Okay.
We're
So I'm not as dumb as I look.
Here.
Yes. The Athabasca River debouche. Well, what's the plural of debouche? Debouches?
It must be. Let's see.
It debouches here?
Debouches.
Well, darn.
Hey, we didn't even have to question it. We just could have kept rolling right through.
We could have. Okay, so I'm not as dumb as I think I am sometimes. Okay, so, but that's important. Okay, all kidding aside, that's important. So let's back out here. Now, why do I have Mount Edith Cavell flagged? Well, I actually should also flag Mount Robson, which is right here. Look at this. There we go. There's Mount Robson. Wow is right. Now, what's really the row is that at the end of the last ice age, at the LGM, remember the LGM, late glacial maximum? The only thing of these mountains that you saw was just like the uppermost peak. That's all you saw.
And how tall is the mountain?
No, geez, let's see. It's got to be, I think, 3,000 feet above the valley floor? I can tell you right here because, well, let's see. I would want to open Google Earth.
It says 3,954 meters.
Meters, yeah, 3,954 meters.
Wow. So that's 12,989 feet.
12,900. So almost 13,000 feet. Okay. So that is Mount Robeson. The other one was Mount Edith Cavell. So I wanted to pull that up too because the very similar metaquartzite rock composes both Mount Edith Cavell and Mount Robeson. I think there has been some discussion as to which one it came from. I think more have come down on the side of Mount Edith Cavell than Mount Robeson, but it's a very similar type of metamorphic rock, the metaquartzite. Okay, so look up now the word Nunatak, N-U-N-A-T-A-C, Nunatak, I think.
With a K or a C? Yeah,
I think it's a K. It's a K.
Yeah, Nunatak. A mountain peak or ridge that protrudes from an ice field or glacier, often forming a rocky outcrop above the ice. The word comes from the Inuit language and means lonely mountain.
Lonely mountain, yeah, because you don't, yeah, right, because all you're seeing is the isolated mountain peaks, and then everything in between is just pull up some images and see, so we can see what it is. Because here we go, because this is what I say, this is what we just looked at, Mount Robeson, it was a Nunatak. That's what British Columbia and the Rocky Mountains looked like at the end of the last ice age.
Wow.
Yeah.
Wow.
Wow is right. That's a pretty... So, yeah, the one you're hovering over there, right there, that's probably exactly what it would have looked like from the air 15,000 years ago.
Wow. Aha, here's that famous Antarctica picture. Everybody calls that a pyramid.
Oh, well.
They don't know about Nunataks, I guess.
No, but here's the thing. It is normal under certain erosional regimes for the end result to be a pyramid-shaped rock, both from glacial erosion and water erosion, both.
Well, you just answered a lot of conspiratorial questions here. I don't even think you realize what you just did to the internet, Randall.
Oh, sorry. Sorry, guys. But, I mean, we're looking, this is normal to the plane of the picture, isn't it? Aren't we looking perpendicular?
Yeah, it is.
So, well, yeah, so.
This is a satellite image.
Yeah, so that's a two-dimensional, essentially a planar surface there, isn't it?
Mm-hmm.
But I see. So there's, yeah, I got it. So, but that actually is very normal glacial erosion. That's not atypical.
Why is that?
Well, it's because of the way. Yeah, I mean, okay. So when we get, I can show you like examples of it. I have photographs that I've taken on trips where you see exactly that same kind of erosion. On varying scales. But you got a picture if you've got a glacier moving through, it looks like up there just above the red flag, right in there. Okay, that would be like a base of the thing. Well, that's a valley right there, right? That valley was occupied by a moving glacier, and that moving glacier is gouging and stripping the bedrock as it's plowing its way through. Now, what you end up with is natural. You can see it in water erosion too. Mm-hmm. What you end up with is a triangular planar surface. I'll pull up some examples and show you here in a minute if you want me to.
Yeah.
Okay, so anyways, but back to this. You got Mount Robeson and you've got Mount Edith Cavell. You've got the Athabasca River debouching from the Rocky Mountain front, turning south at Hinton, and then following more or less parallel. Okay, so here's Mount Robson. Mount Edith Cavell is right down, right here. Now notice that you've got the river flowing here. This is the Yellowhead Highway. Oh, wow. Yellowhead Lake. I forgot that. That's right. Yellowhead Pass. Boy, this is a trip, let me tell you, going through Yellowhead Pass. So this is what Bradley and I did. We followed the route of the erratics train, which was a very interesting thing to do. So we started at Mount Robson and we followed the river on out. And then we came out here and let's see, what did we do? Did we come all the way out here and come south, or was there a road? I need to go back and backtrack because I photographed everything as we went. But anyway, so we followed the route of the erratics train. We stopped in Calgary, and this is where we met Graham Dunlop and Darren Grimes because they were living in Calgary. And the reason we were there is we were on our way to this right here, Okotoks, which I believe, if I remember right, was in the Blackfoot language and meant big rock. Mm. And Okotoks was the biggest of the erratics train.
Wow.
So did you find something?
Yep, I got it.
Okay, so I'm going to stop sharing and let's see what you got. Ah, there it is. In fact, no, that was, okay, yeah, you had the bunch of pictures of it.
Look at that.
Yeah. Let's see. Go back. I wonder if any of my photos are up there anywhere. Let's see.
Oh, there's a good one.
Oh yeah, that's the one I took. That was the first time I was there.
Ah, yeah. This is one rock?
Yes.
Oh my gosh. How big is the rock?
Well, let's see. Tell you what we'll do is we'll go that way. You can see a person standing there.
Right here, yeah.
Yeah, 18,000 tons. So you see how it's sitting out there in the prairie?
Yeah.
Okay, so how far is it from, say, from Mount Robson to Calgary? Mount Robson to Calgary. How far is that? Oh, look, that's a great aerial shot of it.
Yeah. It looks like it's about 495 kilometers.
So call it 300 miles.
Mm-hmm.
So this rock, 18,000-ton rock, boulder of metaquartzite, has been transported 300 miles from its source.
Wow.
Okay, so now when you look at, let's go back to, the legend of Big Rock. So let's go through a little exercise in forensic geology.
I'm ready for it.
So there we go. So this, let's see, you can see Brad Young right here in the foreground. So that gives you a sense of the scale of this thing. It's enormous. 18,000 tons. And we just determined that it's been transported about 300 miles from its source, from its bedrock source.
So those two, so just to be clear, Mount Robson and Mount Edith Cavell, if I'm remembering the name correctly,
yes.
are the only two places where this type of rock is found?
Those are the two mountains that look like either, basically yes. Yes. Okay. I think most of the opinion has been that it was sourced from Mount Edith Cavell.
Okay, so a little bit closer than Mount Robson to Calgary.
Little bit. But you still got a problem. Both of those mountains, as it turns out, are on the west side of the Continental Divide. This is on the east side. So what you have to do now is you have to come up with a means of, first of all, you have to quarry these rocks. Now, this is part of this 500-mile foothills erratic terrain. This just so happens to be the biggest one. The ones we pulled up, we saw those others before. It's the same rock from the same place, right? Now, I don't know what the total weight of all of them is because, there's a lot of smaller stuff strewn in that long 500-mile pathway, right? Mm-hmm. I don't know the total. Somebody may have calculated the total volume of but I don't know what it is. But in any case, you've got this train of this stuff going, it's strewn about 500 miles there from where the Athabasca River debouches at the mountain front by Hinton there all the way down into Montana. So, and the largest one, many of them weigh many, many tons. This happens to be the largest, which weighs 18,000 tons. So let's focus on this one because we can come up with an explanation for this. Let's see here.
Are there any other close to that in scale, or is this by far the biggest?
Oh, this is by far the biggest in the foothills erratics terrain. I'm guessing there's several others that might be 1/4 to half this size.
Still
we could go back.
rock.
I've actually documented it, but it was so long ago. I mean, I've got the charts. I didn't pull them up because I have a whole list of all of the identified larger ones. Maybe 24 3 dozen of them that are of substantial size. You can go, visit them, but none of them are this big. But let's take a look here at just looking at this boulder here, Okotoks. Let's just see what looking at Okotoks can tell us. So describe to me what you see here.
I see what appears to be a cut through, if that's one rock, it's either cut through one rock or a divide between them. It's kind of flat on top, on the left, and on the right.
Yep, flat. That's good, and kind of, I mean, they're.
There's a notch here on the left. I don't know if people can see my mouse, but in that left structure, right in the middle of it, it looks like there's a notch.
Well, that notch goes all the way through.
Okay.
So it's like a crack. It's more like a crack that goes through. So far, I mean, you're pointing out some good stuff there. Now look at also the like positions of the rock. What can you say about them? From looking at this, do you think it would be a safe assumption to think that the surface of these rocks are more or less continuous? Like if, let's say you were looking at a battleship that got blown in two and it's sitting on the bottom of the ocean, right? And you look at, and it's, it's oblique sitting there on the ocean bottom, right? But you would look at that and you would go, well, obviously at some point, this was one structure, right? So if this was one structure, one rock, you basically have to come up first with a way of quarrying it from the Nunatak. Then you have to get that quarried 18,000-ton rock 300 miles and deliver it to this spot on the right where the prairie meets the foot of the mountains. And how do you do that?
I mean, from what we've looked at over the last couple of episodes, I would say that you need a lot of water, and you probably need something to help dislodge it, some type of impact or something like that.
Yes, you would need a force, right? You would need something to separate this, because at one time, obviously, this was part of the mountain.
Right.
It's part of the mountain, right? So, okay, as I look at this, a couple of things that I would point out is that you look at the thickness of the rock here, and that looks like it's a good 30 feet. If you look at Brad, and he's 6 feet tall, is there 5 Brads? I would think that there's 5 of this guy's at least 30 feet tall. Yeah. And you can see over here, it's not quite as high, but by the time you look at this back here, yeah, this looks like it's about as high as the prominence that Brad's standing on, almost. Now, here, you're obviously much closer to the ground. You're probably 15, 20 feet from the ground here, right? 15 feet, say. Now, does that mean that the bottom of this rock is flat and it's just thinner here? Or was it a rectilinear block of rock, and right here, this face of the rock would continue underground about this distance here? Mm-hmm. Same over here. You see what I'm saying here?
Yeah.
Is that, because that is in fact what the case is. Well, you can see right now, this block is not sinking into the ground, is it?
No.
But at one point, a big part of it sank into the ground. And that's what we're seeing here. We're seeing that this was a soft surface, and this huge boulder sank, and as it sank, where did it separate? It separated what would have most likely just been natural fracture lines in the rock. Right? Mm-hmm. So we can reconstruct a scenario here that this surface on the left would match this surface on the right. The thickness of this slab here is continuous. Let's just call it 30 feet. Same here, that this block is a big portion of this block is underground. And now we have to think in terms of how this was delivered. It's likely, I think we've just could surmise, that at the time this rock was deposited here, the ground was soft enough that, like now it's not soft enough. This thing doesn't sink into the ground. There, I mean, could you have enough of a... right.
Not at any fast pace when it's dry.
Right. No, it's not. In fact, in the lifetime of the people living here and the Indians, it has not really, it hasn't sunk into the ground, but it did sink into the ground at some point. And what that tells you is that the ground was unconsolidated. It was probably fluidized, right? Which would be consistent with deposition from water flow, wouldn't it? Mm-hmm. Especially if the deposition of the strata here, of the sediments on the bottom, was followed very quickly by deposition of the rock. Okay, so now how do you get? Okay, so we can see that the rock it was not structurally sound because it's broken into 3 pieces, and those 3 pieces have most likely formed simply because of the effects of gravity on the rock once it was deposited onto this alluvial floodplain here, which was still soft, right? So it was able to sink. but here's, now we could say, well, was it transported by glacier? What are the options for transport? Well, I think there's only, is there two or three? One, we could say glaciers, okay? But in normal glacier, how fast is the glacier moving? If the glacier is moving, 50 to 100 feet per year, which is going to be a typical rate of glacier ice movement, let's just say 200 feet a year. If we've got 300 miles, well, even just from its position at the mountains to the Rocky Mountain front, let's say it's 30 miles. 30 miles, right? Well, so 30 miles is going to be 5,280 feet. And if we divide that by, say, 150 feet per year, well, that's going to take 1,000 years, right? Right? I think, unless I...
No, I think if it's...
Wait a minute. What did I say?
You said 1,000 years, so I think it's...
Let's see, 30 miles will go times 5,280, so that's 158,400 feet. And if it moves 100 feet per year, I'll go 150 feet per year. Yeah, 1,056.
Just about a mile. I mean, just about 1,000 years. Yeah.
About 1,000 years. Okay. Now, in that 1,000 years, let's say you've got to extract, somehow you have to separate this rock from the mountain that it was a part of. Right? And we assume that this happened. Are we fair to assume this happened when there was a big ice sheet and this was a nunatak? I mean, is that an assumption? Or would this have been disconnected from the mountain, say, in its modern condition? Of course, the big problem there is if there's no mechanism, if you were to dislodge an 18,000-ton boulder from one of the flanks of Mount Edith Cavell and it fell down into the valley, it's not going to end up 300 miles away out on the edge of the prairie, is it?
No.
No. In fact, it's probably going to bust into a million pieces.
On its way down, yeah.
On its way down, exactly. So you can begin to see the problem. We're going to quarry an 18,000-ton boulder. We now have to transport it 300 miles, dump it onto the down edge of the prairie, where the prairie meets the mountains, right? Now,
and that's only wait a minute. That's only if it moved 30 miles.
Yes.
1,000 years, 30 miles, which would get us to the prairie essentially.
Well, if it was ice, glacier transport the entire way, now we've got 300. Now you're looking at what, 15,000 years. Okay, now what's going to happen? Let's go back to the 30 miles and say 1,000 years. That means 1,000 years, 1,000 winters of snowfall, right? We can also assume, what is the snowfall going to be greater than now? I mean, because after all, there was so much snowfall and so little melting away that you were able to fill those mountain valleys with thousands of feet of ice, of glaciers, right? So how rapidly is that going to continue to accumulate? So in other words, how much glacial ice could accumulate in 1,000 years? So in other words, in 1,000 years, by the time, if that rock right there is placed on top of the ice sheet, and the ice sheet is moving and it's being transported, I mean, hell, we could double it. It doesn't matter, and say it's delivered in 500 years. It doesn't change the basic scenario, is that during that time, it's going to get buried under 500 or 1,000 years of additional accumulation of glacial ice, right? Mm-hmm. So what's going to happen is that as that overlying ice begins to amass, it's putting pressure on anything that's within that ice mass. Could you, under those circumstances, if this thing right here is entrained within thousands of feet of glacial ice, under these extraordinary pressures, could it be delivered to this site intact? And the answer is, under what conceivable circumstances could this rock not be essentially more fractures, more pulverized under the enormous pressures of the overlying accumulating glacier mass that's going to occur, that's going to accrete over the thousand or thousands of years that it would take to move this rock from its source to where it is now, if you're looking at ordinary glacier accumulation, glacier movement, and so on. So we have to look at something else. And this is where we have to go, okay, it had to have been catastrophic. Now, at the very best, think about this. I want you to look at this picture here, and I want you to look at these edges. Do you see how these edges are very sharp, angular? See that? Okay, well, this would be completely contradicted by end glacial transport, which would grind off. There would be no sharp corners surviving entrainment within a glacier and then being carried hundreds of miles without and still showing up at its destination with this kind of articulated, sharp, angular corners still intact.
So it's not like it was frozen in an ice cube and then slid all the way down here and then it melted.
Pretty much, yeah. But you have to think, if you've got this glacier mass, and in this glacier mass, you've got this dynamic flow of ice, right? So now this rock is put on top of it, and as it slowly moves down, 100, 200, 300 feet per year, with some exceptions because there will be some surge events within there, as it's moving down, it's continually snowing each year. So each year it's accumulating another 3, 4, 5, 6 feet of snow. Then the next year, then it's buried. Then as that continues to accumulate, those layers of snow that came down immediately subsequent to that rock being placed on that glacier, it's going to get buried under first hundreds, then thousands of feet of additional accumulated glacial ice. So that is the problem where we see boulders that we know have been entrained and carried within glaciers. They don't come out with this kind of pristine angular corners. They're ground. You know, think of if you throw a rock in a rock tumbler, right? Well, with the glacier, it's like a slow motion rock tumbler, but the end result is that it's going to shear off corners, sharp corners, that sort of thing. You don't see that here. That's what I'm trying to call your attention to. So you had to have a method of transport that's not going to have that grinding effect on the boulder. It has to be transported more or less pristine. In other words, these fracture lines here are only slightly younger than the fracture line that separated, let's say, this face here from the original mountain. And there's been very little erosion on it, right? It was carried this far, 300 miles, set down in this floor of unconsolidated alluvium. It came in with its angles intact. How do you do that? Well, several things happen to be simultaneous. The only way you're going to get this rock here carried, you can't bring it in the water itself, right? Because if the water is turbulent and forceful enough that it's transporting, that this 18,000-ton rock could be transported within the flow, well, it's going to get busted up long before it gets here. It's going to get busted up in the first 10, 20, 30 miles of transport. Boom, that rock, by the time it got to here, it's gravel, see? You're not going to have this, not in water transport. So we can exclude that. We can exclude end glacial or within the glacial transport because wouldn't necessarily turn it into gravel, but it would definitely grind it up, and it would start with any sharp corners, any angularities, any fresh exposed rock is going to be the first that succumbs to the slow motion tumbling and rolling of the block within the glacier mass. So what does that leave? Well, it couldn't be transported. I think we can exclude transport within the glacier. It's certainly not going to be under the glacier. That's not going to survive. It had to be on top of the glacier, right? But that glacier has to be in water. It has to be an iceberg.
Okay, yeah. So it's on
Right?
top of the glacier. or it's an iceberg essentially moving through. I mean, I would guess rapidly moving water.
Yes, that's loaded with sediment.
And it's dropping all of these rocks along the way.
Well, what you picture is a very large flood, choked with sediment, choked with icebergs. And on many of these icebergs are the remains of this Mount Edith Cavell. Rocks that have been quarried from the mountain, which we assume at the time was a nunatak. So if you know, and of course, all of these assumptions you can go into them much more specifically. And, you know, when you begin to really look at each one, each one seems to have evidence in its favor. What we're describing here is somewhat speculative, but it's consistent with what we know about the whole process. But there are big blanks, like by what process are the original rocks excised or disconnected from the original mountains, placed onto the ice. And what it looks like is you have a scenario that would require almost instantaneously the emplacement of the boulders onto the ice, the fracturing of the ice, and the melting of the ice. The melting of the ice provides the flow that then transported the icebergs, which were the fractured pieces of the ice that were, so you had part of the ice sheet basically smashed into icebergs. Presumably the same force smashes the Rocky Mountain peaks that are now shoveled or avalanched out onto the ice sheet itself. Mm-hmm. The ice sheet is undergoing massive melting. And so now the broken pieces that have the massive boulders avalanched onto them are now being swept down into the meltwater flow. It discharges from the Rocky Mountain front. Topography directs it to the south. And most likely what happened was when you, on the other side of the of this corridor through which these erratics are strewn, stood the Laurentide ice sheet front. So the water couldn't just flow to the east because the front of the Laurentide, the Great Laurentide ice sheet, stood in its way, which would have deflected the flow to the south. So interestingly, the Foothills Erratics Train defines the same thing that is known as the ice-free corridor, which was assumed to have been a passageway for the migration of both people and animals. And this probably would have happened pre-Younger Dryas.
So to the east of the ice-free corridor, is there more glacial structures? Is there more glaciers?
Well, yeah, I mean, there's moraines, huge moraine deposits that were created by the Laurentide ice sheet. And we can see some of the rocks that are in that have been transported hundreds and hundreds of miles from further east, carried by the glaciers and then dumped as terminal moraines immediately to the east of the erratics train. So you had these two great ice sheets, and they met. The Laurentide, the bigger of the two, centered over Hudson Bay, reaching all the way to the foot of the Rocky. You see, and in fact, during the late glacial maximum, there was no ice-free corridor. The Laurentide and the Cordilleran ice sheets, they met and flowed together. This did not happen apparently then. But again, it says this was about 14,000 and 15,000, and we saw 14.9, and I was suggesting 14.6. But that remains to be seen, because if it's 14.6, then it puts this exactly consistent with Meltwater Pulse 1A. So let's kind of put together what we've got here. We have to contrive a scenario that will fracture huge amounts of bedrock, let's say Mount Edith Cavell, avalanche this stuff out onto the glacier surface. Then the glacier has to be broken, because the only way you're going to transport these boulders from their source is through iceberg transport, just like we know has happened and we've looked at and documented and we've seen the evidence for that mode of transport in the Channel Scablands, right? Yeah.
Right.
We saw boulders there that were transported by icebergs. And we saw some when we learned about berg mounds. Remember berg mounds?
Yes.
Right. Because let's say you've got a big dirty iceberg, but you don't have a boulder sitting on it. But then that dirty iceberg comes to ground, it melts, and all of that dirt and debris and gravel and everything that's in it will make a pile.
Mm-hmm.
And you can trace these piles once you know the genesis of these piles over the landscape, that they're berg mounds. That's one of the proxies we use for, at least up in the glaciated terrains, to identify flow pathways. You know, okay, if you see a field full of berg mounds, you know, okay, there was a current flow that swept over this. There were icebergs in it. Those icebergs came to ground. So what we've been able to deduce now from all of this, what we've looked at, okay, we're looking at water transport, and that is confirmed by the fact that the valley floor would have, the valley floor is consistent with having been unconsolidated alluvium, which if you've got the water flow, it's going to be choked with sediment, right? Within, it's not clean water at all. It's dirty water. And when that flood water subsides, it leaves behind essentially a big, thick layer of mud.
Mm-hmm.
So now, here's what you can picture. You have to come up with a source, a force, an energy that can virtually simultaneously fracture the flanks of the mountains extending above the glaciers in the form of nunataks, fracture those, avalanche them out onto the ice. At the same time, huge volumes of that ice are being melted, and then there's enough of a current that current is taking these chunks of ice and washing them out, washing them through the Athabasca Valley, discharging at the Rocky Mountain front, washing up against the wall of the Laurentide ice sheet, and being deflected to the south. So all of this stuff is surging out. Let's go back to the mountain. I mean, to the
map.
The map. So I'll stop and then I'll reshare. I'm getting really good at this.
Yeah. Well, you might want to keep going on this point, but I have a question about it. I mean, what did they find underneath the rock? Has anybody looked underneath?
No, I don't think anybody's excavated under it. I mean, actually dug under it.
Any scans?
Yeah, there've been some stuff. That's why I can say that this is like a thick part of this rock is actually buried underground. Okay, we're now back here. Let's go to Mount Edith Cavell. Okay, let's say that we go in here and we look and we see several. Let's focus in. I hope it focuses it better than this. But we can see several places that look like they could be good candidates. Like, look at this. This has been scooped out here by glaciers. Let's see if we get some pictures of Mount Edith Cavell. There we go. So those rocks came from somewhere, were part of this mountain once. And they would have been from up near the top, because the assumption is that at the time they were quarried, most of these valleys were completely filled with ice. So it'd be interesting, and I haven't done this, but I would guess you could go maybe using OSL, looking at just the geomorphology and actually finding the spot where these, if you were to play this film backwards, 15,000 years, and then see this stuff going back up and then becoming part of the mountain, where exactly was it? I don't know. But you can actually see, and I have looked on Google Earth. We maybe should pull that up in a minute. Let's see if I close this out. Maybe, is it going to focus for us? Well, there's plenty of candidate locations of where this sculpting could have taken place. But you have to transport it through this valley here, and look at the floor of the valley. You see these long linear trends? And look up here, you can see, oh, yeah, here very clearly the results of this catastrophic flow through this valley. You can see it very clearly right through here. So you had water flows coming down. Let's see, there's Mount Robson right here. Oh, yeah, now we're getting it. Now we're starting to get some resolution. So it could have been anywhere along this, probably along this southwestern flank. That if Robson was the source, this southwestern flank looks like it would have been the most likely location. Like, look at this right here. This could have been quarried out right here. Google Earth could probably tell you something. But in any case, either way, you can see that the rivers converge right here and then flows up to the north. And, oh, look, you see the flat floor here? That's all sediment left. Comes out this way. And we should be able to actually find the channels, probably, let's see, through here, because I don't know exactly where the Laurentide front was, but it was somewhere out in here. And that's why the water couldn't keep flowing east. It had to get turned to the south. And then Okotoks got dumped here. So there would have been a very large iceberg necessary to transport Okotoks. So the size of that iceberg might give one a idea of the magnitude of this flow that's coming through here, because that iceberg is probably the size of a tanker ship that's carrying this as its cargo. Now you got to picture that the final stages of that process is that the iceberg is being swept along in the flow, and because it's the biggest iceberg, it probably was one of the first ones to come to ground. But so the iceberg comes to ground literally, right? It stalls at some point because as the floodwaters are declining, it's losing its competency to transport mass. So the first thing that settles out is going to be the heaviest and biggest stuff. So the iceberg comes to ground. It's in a bed of soft material, but then the iceberg itself has to melt away. Now, it might take years for that iceberg to melt away. But bear in mind that that iceberg melting away is also going to keep the substrate, the ground underneath, perpetually wet and soft until the iceberg is gone, and then the modern climate regime can come in and all of that. But so the final stage of this process is actually rather slow and gentle, because the force to create this flood and the armada of undoubtedly hundreds or probably thousands of icebergs being carried along, the water flow had to be enormous. There had to be a lot of icebergs because every iceberg isn't going to be carrying a rock. So you probably got, for every rock, you probably got 10 or 20 or more icebergs being carried along in there. But there's enough rocks to show that there had to have been more than just melting of the glaciers, because you have to impose enough force that you're going to fracture the flanks of the mountains, the shoulders of the mountains protruding above the ice sheet. So how do you do that? I don't know, other than I could speculate, and I would speculate some type of an impact event, whether an atmospheric explosion or actual impacts. But where would you look for actual impacts? I don't know, other than if we go north of here, you'll notice you've got this long trough, and you can see that the valleys are all interconnected here. See this? Look at this. Okay, but then you trace this channel north all the way up to here, and you get up to Prince George. And all of this area up in here, let's see, where's Prince George? Let's zoom out. There it is, Prince George right there. And there's something interesting going on when you start looking at the landscape around Prince George. And here you can see what we're getting into. Do you see what we're looking at here?
Yeah. Chevrons.
Drumlins.
Drumlins.
Thousands and thousands of drumlins. We've looked at drumlins, haven't we?
Mm-hmm. I think we've actually looked at Prince George very briefly before.
Mm-hmm. Now, drumlins are a paleo current indicator. They can tell us which way the water is flowing. The blunt end faces of a drumlin, the blunt end faces up current, faces upstream. So if you're looking at this, what was the direction of flow that sculpted these drumlins?
The blunt end faces upstream.
Yes, the blunt end faces the direction that the current is coming from.
Yeah. Well, they're coming south.
Do you see a blunt end? When I say blunt end, look at this right here. This is blunt. You see this? This is the blunt end, and then you have a tapered end. Look at these. These are more clear. See, the south ends of them are blunt, and then they taper as you go north. So this is telling you which direction. Now, these are subglacial flows we're talking about. This is a movement, massive subglacial water movement has created this landscape that you're looking at here. And which way is this flow going? It's going south-southwest to north-northeast. And it's coming right up here, headed like it's going straight for Prince George. And you see that over here, the top end of the Rocky Mountain Trench, and it goes all the way down, all the way down, all the way down, all the way down to Flathead Lake. And then it opens into the basin here. The Mission Basin, it's called, because these are the Mission Mountains here. And at the south end of Flathead Lake, you've got this hummocky stuff, which is terminal moraine. And I think we've defined terminal moraine, haven't we?
I believe so. I know we've defined moraine.
Right. There's more rain, and then there's less rain. And if you have no rain at all, it's known as a drought.
Right.
Okay. Good. I'm glad you're straight on that.
Thank you. Thank you.
So
what is terminal moraine? Just to be clear.
So we'll look it up. Terminal moraine. So first of all, let's define moraine. Moraine is the ground mass that's created by the glacier grinding over and pulverizing the landscape. The terminus of the glacier is where the snout of the glacier, where the glacier ends, right? That's also called the zone of ablation. It's where the tip, the end of the glacial tongue tends to melt back as fast as it's growing, right? The moraine that piles up at the glacial terminus is called terminal moraine. So right here you have terminal moraine. And what this terminal moraine that you see right here does is it tells you that this was the southernmost extension of this lobe of ice, because here's the moraine right here. And you can go through it. I've been through this many times, and we take groups to outcrops to show there's some great outcrops where you can just really say, okay, this is moraine. Doesn't seem very interesting because it's just there's nothing there except a jumbled mass of incoherent stuff. Chaotic stuff from sand to gravel to cobbles to boulders to other kinds of stuff, but mostly that. And there's no structure to it. There's no architecture. There seems to be no stratification to it, and that is how you distinguish a deposition from a glacier, because it's a structureless mass from the deposition of water that will usually have some kind of architecture within it. Showing bedding and sorting of the constituents of the deposit, right? So structure, architecture in water flow, chaos, no structure in glacier flow. So moraine, But see, here's where drumlins get interesting, because drumlins start out as incoherent, chaotic, jumbled, pulverized glacier mass, subglacial mass. But then you look at a drumlin field, and there's structure to it. Like, just compare what we just saw with drumlin swarms compared to this. Well, there's some structure here, right? You can kind of almost see that there's kind of a recessional effect going on right here. Mm-hmm. So you've got this mass here, and then probably a short passage of time, because this glacier is now melting back, right? After the catastrophic disruption, which completely causes the conversion of large amounts of glacier into, first of all, water, and then, of course, solid chunks of ice. But then after a period of time, the point I guess I'm trying to make here is that we could estimate maybe a quarter, maybe a third of the I don't think as much as a half of the glaciers are destroyed in these convulsive events. Because what happens is, it seems like the convulsive event separates two glacier regimes. One is that prior to that, the glaciers are living glaciers. You have a zone of accumulation, you have a zone of ablation. In the highlands, the glaciers are accumulating. Mm-hmm. Each year's mass of snow adds to the growth of the glacier. The weight of that pushes on the glacier and causes a dynamic flow downhill, all the way down to the snout of the glacier, where most of the melting takes place. In between the zone of accumulation and the zone of ablation, there's this inflection point, the equilibrium point, where the transition occurs from the glacier growing to the glacier shrinking. Right, that's called the equilibrium line. So in colder times, the equilibrium line goes up. In warmer times, the equilibrium line comes down. Okay, so if it comes down, it's going to be more readily melting. But in either case, you see what you've got right here is terminal moraine. We can zoom out, and we can go, let's go up here. We can see, here's another example of terminal moraine. So what happened was, you had this major glacier lobe coming down, and it trifurcated into three sublobes. One of them got diverted right back to the northwest. One of them got diverted to the west, and another one got diverted to the south. The one that diverted to the south left its calling card in the form of this moraine, called the Polson moraine. This lobe terminated right here. You can see, look, here you've got the flat outwash plain that was in front of the glacier snout, and here's where the glacier snout was. Mm-hmm. So all of this right here is lateral moraine, because it was on the side of the glacier. Then this is the terminal moraine right here. And there was a natural breach of meltwater through that terminal moraine, which provided the most convenient and economically feasible place to place State Route 28. So here's an example of, humans coming by thousands of years later and taking advantage of the features in the landscape that were created by these natural events. But interestingly, there was another major flow. We looked at this, came down right through this way, and just like when, the glacier lobe was here. So when this water flow came down and hit the glacier lobe, it was diverted to the west, and you can trace its path right down this way. And it flowed out. So if you were looking at this over at the time this flood happened, this would have been a Nunatak right here, right? All of this was buried under ice, and now you've got this major subglacial flow coming from the north here.
So why did it divert to the northwest? Why did one of the lobes divert to the northwest?
Well, I would imagine that, if you look at this is a smaller lobe than this lobe, and that's a smaller lobe than this lobe.
I see.
Right, and it was probably just because, if you can see here, the mountains are bottlenecking. So that means that the ice would have been piling up here, right? It's being fed from, the ice is continuing to flow south. The big main trunk has got this big glacier flowing south, right? Well, when this diverts to the west, what's happening, it's trying to go into this V-shaped valley. You can see how the valley is getting narrower. So that causes the ice to pile up. And when it does, the path of least resistance probably was this to the north. However, when that lobe did divert to the northwest, it left its own hand, sculpting of the landscape. And I mean, you can see where the glaciers ground their way around this way. And then you can come up here, and here's terminal moraine right up here. Right? And then you had this huge flow that came down, and prior to that flow, this ridge would have been all connected. So this island wouldn't have been an island. It would have been a continuous ridge going right up here. This right here now is a 500-foot cliff. This trough, you can see this was a spillway right here. And right here where there's a lake that occupies the bottom of this trough, this spillway trough, because as the water rounded this curve, it was particularly turbulent. And because it was turbulent, it was able to erode up the bottom of the channel quicker, you see. So you've got a scour trough right here, and there's another one right up here. So this was a water flow pathway. So you can chart all this, and this is where Google Maps and Google Earth and all comes in so handy. Because, a few generations ago, we didn't have these tools. So all of this is just this clogging of sediment that occurred between the mountain ridge here and the thick glacier lobe here. So you had this trough between them. So that became a conduit, and it flowed down, and the whole floor of this valley here has all of the sculpting of the sides show the turbulent vorticular motion of the water as it's moving through. It was choked with sediment because when the floodwaters finally subsided, it left this flat area here. And if you were to dig down, if you were to flush all of this out, you would have seen that pre-flood it was a V-shaped valley floor. And if you filled this up, I don't know, 200 to 300 feet, there's probably 200 to 300 feet at least of a flat sedimentary floor in this is called Big Draw here.
Okay.
And on our Montana tours, we follow this route because we follow the route of the floodwater.
And so then it filled up with 200-300 feet of sediment, making it flat.
Yes.
Yeah.
Yep. And then, look, the water gets diverted to the south right here and flows down through the Little Bitterroot Valley.
And it's diverted because is there a glacier there, or is there some type
yes,
of
there's
rock?
the glaciers would have been probably, right in here. I don't know exactly where they were because part of the problem is, and I haven't been up here. This could be remnants of moraine here. I haven't been up here. I've been down 28 many times, but I've never gotten out and explored intimately this area up here. But it's likely that, if you picture this is buried in glaciers here, that glacier line is going to come across right in here. So, yeah, you're going to have these mountain glaciers that are part of the Cordilleran ice sheet. This is probably where they stopped right here. Right? It would make sense because right here, the glacier lobe is usually going to project further south than just the normal edge of the ice. You'll have the normal edge of the ice sheet, and then in places where the topography is conducive, you will have these tongues flowing off, right? And so those create those glacier lobes. So it's most likely what you're going to have is the glaciers are covering these mountains, but there would have been enough open area in the valley here that this water came down, rushing down, and then it hit these hills right here. And you can see that there are several places where the water breached the hills, right here. And here you see some scour trough lakes right here, Schmidt's Lake. Where else? There would have been a flow that came down this way as well. And if I go to satellite view and I zoom in, we looked at this. Remember this?
Yes.
There's your giant current ripples.
Mm-hmm.
And you can actually see there's multiple megaflows coming through here. So look at this. Here's a megaflow coming through here, right? Here is a megaflow. You can see it, look, two flows right here. Here's one. They're almost conjoined right here at the hip, and then they separate down here. The peak here of the depth of this water through this Camas Prairie here was we can know, because we know the elevation above sea level of the basin floor, and we can trace the high water mark up on the valley walls, and on the mountain walls the high water mark was at 4,200 feet above sea level, 4,200.
Wow.
So the valley floor is 2,800 feet above sea level. So from that, we can determine that it was the water at its maximum depth coming through here was 1,400 feet, 1,400 feet deep. And it's 5 miles wide there, and it's probably moving at 40 to 50 miles an hour. And it would have been choked, again, with icebergs. But see this, so now we've kind of raised an interesting question. I've kind of showed you this connection now between the Rocky Mountain Trench, at its south end, is feeding into Lake Missoula, and at its north end is up here on this interesting terrain up here that's characterized by these massive drumlin swarms. Now, could all of this be related to what's going on over here with the foothills erratic strains? I would say it's almost 100% certain.
It would be quite the coincidence if not.
If not, yes. But you see, here's the thing. Here's again, mainstream. Doesn't, just like in the same way, Bonneville flood and Missoula flood are two separate, unrelated events.
Yep. Here's another one.
Here's another. This event, if we want to call it the Calgary flood, or the Athabasca flood. I call it the Athabasca flood because of the Athabasca River.
Right.
Well, is that also unrelated? But if it's related to the Missoula flood, and the Bonneville is in some way related to the Missoula flood, then they're all three related to each other, aren't they?
I would think so.
One would think so. Let's go back to my other screen.
Yeah, this might be jumping ahead here, but are we looking at Prince George as a potential point where that catalyzed this?
Well, I think that, yeah, and in fact, that's exactly where I'm going with this. Okay, so let's just continue on with the slideshow. Next slide. See the yellow line? That represents the Alberta-Montana state line. You see what we're looking at here?
It looks like
ripples. A giant ripple train. And you see this white line here?
Mm-hmm.
That's a mile long.
Whoa.
So these are massive. Well, if you go back and you follow the erratic train to where it passes into Montana, this is what you see. So this to me is confirmation that, we're talking about really large water flows.
This is further west?
Further east.
Further east.
Further east, yes. In fact, it's the Milk River that flows through here. So let's go back up where you can see where Calgary is. Mm-hmm. So the train comes right down this way, comes over, and you can actually start seeing there's a pathway right in here by Milk River. And if we zoom in, let's see if I can catch this on the first attempt. Let's see. If we zoom in, let's see. We should be able to see them. They're right in here. Let's see. Where is it? They're right in here. You can see the giant ripple train. Milk River. Okay, maybe it's over here. Let's see. Yeah, there it is.
Yeah.
Right, there it is. So that water flowed down this way and passed over from Alberta into what is upper Montana, and you can see where several places it starts down-cutting channels. And we have, if I go back to here, let's see here, Milk River. We should be able.
So
there. Look, so this should be recognizable to you now.
Yeah.
Underfit River, right?
Yeah.
A modern. So this is the Missouri River. So, in other words, this flood that came from these melting huge ice sheets over the Continental Divide washed down along the east of the Rocky Mountain front, loaded and choked with gigantic icebergs that were loaded with huge boulders of metaquartzite that came most likely from the flanks of Mount Edith-Cavell, strewn for a line of 500 miles along the corridor between the Cordilleran ice sheet and the Laurentide ice sheet, at the end of where we see that right there where the erratic train stops is pretty much where we start seeing the giant current ripple field. And then that goes in and begins to carve down the valley that is now occupied by the Missouri River. So ultimately, where was all this water headed? It was headed for the Gulf of Mexico. So if you were in a raft sitting on the glacier next to Mount Edith-Cavell and somehow you survived, the end of your journey would be the Gulf of Mexico.
Hey, I'll take that journey. I'd do it for the weather.
Yeah, well, maybe I'd take it like the second half.
Yeah.
Not the first. But so you're beginning to get the picture here, I hope. Is that, okay, so now Missouri River, right? When you think of the Missouri River, you're not necessarily immediately, the first thing that pops into your mind is not any of what we've just looked at here.
Yeah.
Gigantic catastrophic floods sweeping over the land, probably hundreds of feet deep, carrying gigantic icebergs by the hundreds or probably thousands, right? You're not picturing any of that, but that essentially is realistically the scenario that created what we now see as the end result. The Missouri River Valley, the giant ripples, the alluvial floor, the giant boulders that had to have been transported by icebergs, etc. So that's what we're trying to get at here with why we're calling this the big picture.
Yeah.
And you see how we've just now outlined a whole nother piece of this puzzle that we've now put into this emerging storyline or scenario, whatever you want to call it.
Yeah. Yeah, I mean, it's very, very... I mean, last time we talked about this, last episode when we talked about this, it was so much information, and I was kind of foggy on where we're going with this because we had talked about Prince George a long time ago. We had talked about Bonneville, but this is, I would say I'm guessing the picture expands farther beyond this, but this has painted a much more clear picture where at least we have an idea of what could be the catalyst of it before we were looking at what the consequences were of something that we weren't quite sure where it was coming from or what it was.
Well, let's do a little bit more forensic geological thinking.
Let's do it.
Okay, so here we're back to the Drumlin swarm. Are we still sharing screen here? Okay. Remember I said that the blunt end focus is facing upstream.
Yep.
So imagine that you've got a bridge pier and that water is flowing down and it hits the bridge pier and it cuts around it, right? In a sense, it's like that. So this is a water flow that's flowing from down here going this way. Well, where's it coming from? If I zoom out, where's it coming from? Where was the source of this water? Now, this was a lot of water that created this Drumlin swarm here. So either there was ice there or there wasn't ice there. Now, the theory is that drumlins are formed by massive subglacial flows. So once again, now what we have to assume is if that's correct, then there was ice here, a lot of ice, thousands of feet thick. But at some point, there was this huge onrush of water headed essentially towards Prince George. But where's it coming from? And then we've got this long linear feature here, and we've just seen what happened in here, right? Now, is this creation of the Drumlin swarm connected with the creation of the foothills erratic terrain?
I would think so.
Well, how do we tie them together generically then? Well, if there's water coming from the southwest, where's it ultimately coming from?
The ocean.
Well, it would have to be salt water. I don't think there's any evidence of marine.
So there must be some type of water feature.
Well, remember,
melting
there was a
glacier
whole lot of glacier over here. Probably, a couple of thousand cubic miles of ice minimum over this plateau region. Probably way more than that. Probably 10,000 by the time we figured it all out. Well,
10,000 feet of ice sitting right there then.
I don't think it would have been 10,000. Probably more like 5,000, probably a mile thick on top. Because sometimes up on the high uplands like this, the ice is not as thick as it actually is in the valleys. So for a while, this Drumlin orientation confused me because my research led me to think that Prince George was an epicenter. Because for one thing, like look over here, you can see the direction of flow in all these cases. Look at these scour trough lakes. Now, if they're not exclusively sculpted by glaciers, there would have been water as well. And if you look here, you'll see immediately to the west, your orientation is east-west. As you go to the northwest, the orientation is northwest-southeast. Right. Of course, here we have the mountain blockading. So you've got this long trough here that goes right on up. It's almost like it's a continuation of the Rocky Mountain Trench. You see that?
Mm-hmm.
But the eastern flank of the Rocky Mountain Trench here has been obscured. Why? Well, that's speculation. There's a lot to still be teased out of all of this. But in either case, we have this very large subglacial water flow here flowing towards Prince George. Well, that would seem to contradict the idea that Prince George was an epicenter, wouldn't it?
Yes.
Unless that was not the original flow direction. Now, in order to try to make sense out of this, I took a look at ocean impacts. So what happens in an ocean impact? Well, and there are laboratory confirmations of this. If you fire a projectile into the water, it penetrates the water, it creates an outward expansion of the water and leaves a void, a transient crater, it's called. If the object is big enough and has enough force, the transient crater will go all the way to the bottom of the water column. Now, if that's an ocean that's a mile deep, it might take an asteroid, maybe 1/4 of that in diameter, to penetrate a full mile of ocean water and actually hit the bottom of the ocean, right? And leave a crater, right? Except this is going to be very different than an impact of the same sized object on land. Why? Well, you've got the water. Mm-hmm. So instead of a crater form that may last for thousands and thousands of years in the aftermath, you have this water crater, transient crater it's called, that only lasts for, maybe minutes. It depends on the size of the projector and how much water is displaced by the passage of that object through the water column. Well, it's going to rush outwards, isn't it? But is it going to keep rushing outwards indefinitely?
No.
No. What's it going to do? At some point, it's going to stop, reverse directions, isn't it?
Yeah.
And it's going to flow back in. I think that's what we're looking at here. There's even a term. It's called the resurge wave. So after the hypothetical, and we know from actual the very limited discoveries of craters on ocean bottoms that one of the things that will happen is the resurge wave, like if the same crater was on land, there might be a prominent, very easy to distinguish rim around the crater. But with the resurge wave, it can wash away a lot of the upraised rim. Makes sense, doesn't it?
Yeah.
Because this onrush of the water back into the cavity is going to be pretty darn forceful and turbulent, isn't it? It might leave vestiges of the ring that could be identified, but just like we saw with the Elmo moraine there was a breach. Remember, there was a breach. 28 went through that breach, right? Yeah. Well, in the case of a resurge wave, it would create multiple breaches on the crater rim, but it might actually leave enough of the crater rim that you could reconstruct it. But in any case, it's going to largely make it much more difficult to identify the crater rim. The other thing that it's going to do is it's going to wash a lot of sediment back into the crater. So not only is the water going to lower the rim and obscure the rim, it's also going to dump material into the crater form that fills it up. So now the crater isn't nearly as prominent as it would be had the same event occurred on land. Makes sense, right?
Yeah.
So what I would speculate here is that we have some force that was able to drive this water under the ice subglacially, but it was only able to travel so far before it reached its limit, and then it reversed directions and started flowing back. So only field research, I think, would determine that. But if you go here, you're going to see you've still got drumlinoid forms in the landscape. So you're still got, and they're still blunting. The flow direction has changed somewhat. You can see, look, the orientation is this way, and then up here it's more this way, isn't it? Mm-hmm. So what needs to happen is there needs to be a lot of field work, probably LIDAR, because a lot of these drumlin forms, you can't see them because they're under forests, which is frustrating because a lot of you can drive up there, right? You can drive. I've driven through this drumlin field right here, and you can't see any of it from the ground because it's all forested over. So there needs to be field work and probably, high resolution mapping to figure out where that reversal of current direction, like maybe look at this rim right here, that might be a candidate for the reversal point. And we can go to Google Earth. Yeah, look at here. Okay, so you've still got water flow to the north there, but now you lose the drumlins down in here. So in any case, we've been talking about drumlins, and I showed you the Wisconsin drumlins, didn't I?
No.
Did we see those? Okay, so I'm going to come here just to show you examples of drumlins. Green Bay, right? Here, this is called the Door Peninsula coming up into Lake Michigan. This is Green Bay coming down here, and then this is Lake Winnebago. Now, if I zoom in, let's see, I'm still on terrain, aren't I? Yeah, okay. So there was a trough. You can see that this essentially is a gigantic scour trough. There was a huge water flow coming under the glacier here. Lake Winnebago would have been an extension of or a part of this same trough that is now occupied by Green Bay. Okay, but this is a bunch of sediment that got dumped in here. So if you were to sweep this sediment out, though, you'd have one continuous channel down here. So there was a water flow coming this way. And then it flowed down here, let's see, by Beaver Dam. And let's see if we zoom in here.
There we go.
There we go. Look at this. Drumlins. Now, these are interesting because they're a little different. They're not as blunt, but they're definitely drumlins. So we're still under the ice sheet here, right? This is not a water flow with a free surface. It's a water flow. Now, notice the change in the orientation.
Right.
Right? That's very prominent. Well, what it's doing is it's converging from a point right up in here. You can see it's a single channelized flow that then spread out. And most likely as it's getting near the margin of the ice sheet, the ice is getting thinner, right? So what probably happened here is that as you go north, the ice is getting thicker and thicker, and the water flow was not enough to cause the uplifting of the ice. But then, as the overlying ice mass thinned, it became possible for the water to literally, temporarily uncouple the ice from the substrate. And then right there is where the, rather than being forced into a single channel, the water can now spread out because there's been a pressure relief. The water spreads out, it starts carving the drumlins, and then it discharges from the edge of the ice sheet, and then it's got a free surface. And without that overlying pressure, it's not reshaping the drumlins, reshaping the ground mass into these drumlinized forms. I hope all this is starting to make sense.
It is starting to make sense. So, okay, this is another example of a lot of water flowing at rapid speed underneath a glacier.
Underneath, yes. And did we look at the New York drumlins?
No.
Oh.
We've stayed on the West Coast for the most part.
Okay, well, we're going to come back in here, and we're going to look at Lake Ontario, right? Now, if we were looking at a bathymetric chart of Lake Ontario, which I have one here, I could actually pull it up, but for the sake of keeping the moving here, there's a basin. The deepest part of Lake Ontario, it's called the Ontario Basin. It's right in here. Okay, now we come south of there, and you can see the Finger Lakes. Now, if anybody's watching this that's up in New York, you know the Finger Lakes. They're beautiful. I've been up there. I can't wait to go up again. Because the story that it has to tell here is very, very interesting. But I want you to take a look here, like at Lake Seneca and Lake Cayuga, the two of the biggest of the Finger Lakes. See how they're long trough-like lakes, right? Now I'm going to just zoom out, and we're going to go all the way back over here to Washington State, and we're going to zoom in on Upper Grand Coulee.
Long trough-like lake.
A long trough-like lake. Roughly the same width, the same length, and the same depth as Lake Seneca and Lake Cayuga. Now, could the genesis of these features be the same? Well, we accept a catastrophic flood origin for Grand Coulee, don't we?
Yes.
Now, that lake that you see in Grand Coulee is an artificial because the coulee, which is just a big, long, dry trough, serves as a useful, valuable receptacle as a storage reservoir. So Grand Coulee Dam is siphoning water out of the Columbia River and storing it in Upper Grand Coulee. But one of the things that by doing that, it turns that Upper Grand Coulee into a lake, and it really kind of emphasizes the similarity between Grand Coulee and Lake Seneca and Lake Cayuga. These long, and then another we're doing some more forensic geology here. Look at this. You'll notice that the Finger Lakes, look at the orientation. Let's see, I forget the names of these little ones. I did know how to pronounce this once. But anyways, you see these smaller lakes in here, right? Now you'll see they're oriented, right? You also see that they partially occupy these troughs that have been incised into the landscape. Well, where have we just seen that?
The other side of the United States.
Yeah, up there in Montana.
Yeah, in Montana.
We saw erosional trough. We saw that there are lakes occupying those erosional troughs, and now look what you got here. Coming down all the way down here, and you've got all of these interesting erosional features. Watkins Glen, Montour Falls. Oh, man, these are magical landscapes down there. But notice again here what I'm trying to get you to see. Notice the axial orientation of this lake, Canandaigua. Notice that. Then notice this. Notice this, and then you see how. Just hold up your hand like this and think of your fingers as being Actually, it would be upside down like this, right?
Yeah, the Finger Lakes.
The Finger Lakes, perfect, right? But notice when you hold your hand out like this, they're all converging back onto, it's one hand. They're not, your fingers are not independent, distinct entities. They're all part of your hand, right? Part of this greater feature right here. Well, so if you follow that orientation, what it does is it takes you right to the center of this basin. And I can pull up a bathymetric chart that I have of Lake Ontario, and it stands out really clearly. But then you have this region between the south shore of Lake Ontario and the northern ends of the Finger Lakes. And when we zoom in on that area, look at what shows up.
Drumlins.
Yeah, thousands of them. Look at this. I mean, this is extraordinary. And see, this is here, and people just don't know. People don't know what's hiding right under their feet, what's in their backyards. But look at this. When we go here to the west, what do you see happening with the Drumlins? Let's see. Look at this.
Orientation change, just headed right back to Lake Ontario.
Yes. This essentially is the same radial orientation as the lakes. What is this telling us?
There might have been something that okay, so what happens when you shoot something? Let's just say you shoot something. It's gonna spray like this, right?
Oh yeah.
So maybe it's pointing to Lake Ontario.
Okay, so I'm going to stop sharing for the moment. You know what? I think I might have that. Let's see here. I may even have that. Let's see.
Okay, so now you've taken me to eastern United States, more east, Wisconsin, Michigan, New York area. But you've left me interested in how they connect. And in the western United States, British Columbia, well, it's really British Columbia.
Yeah. Well, that's right. That you're going exactly where I want you to go. I'm leading you right up to the precipice of the rabbit hole. And I'm hoping you just before you realize you've stepped off the edge and you're plummeting into down the rabbit hole is non-reversible.
Well, I feel like if I start speculating here, you're going to drop some other evidence on me that makes me feel like I should have waited for it before I started speculating. But I'm starting to see a larger picture here.
Okay, I'm going to show you. This will help. This will help, I think. It certainly pertains directly to what you're trying to do. We'll go back here. There we go.
Okay. This is what I like to see. We've got a much larger picture here of North America.
Okay, so right here, look at this. Athabasca floods. Look at the arrow. It points right to that, right where the Athabasca River debouches from the Rocky Mountain front. We got the Missoula floods that we've already talked about. Here's the Basalt Plateau down here. The Bonneville flood, pointing here to the Snake River Plain. Ultimately, it originated right here at Great Salt Lake. But look what else we got. Silver Lake, Soda Lake, Manly, etc. Valles Caldera overflow here. Southern Appalachian pluvial floods here. Lake Wisconsin here. Ontario megafloods here. Superior floods. Lake Agassiz superflood. Mackenzie River cataclysmic floods right up here. Now, there's more. I could add more to this, but those are really the biggest of the flows. As it says here, partial listing of various terminal Pleistocene megaflood events in North America. So what I'm suggesting here is that we really need to look for and ask this question: is there a coherent model that can link all of this? Or do we have to single some things out and say, okay, well, Southern Appalachian, that didn't have anything to, that was something completely independent, right? Or Lake Wisconsin, what was that? Or Valles Caldera overflow, right? What are those? Well, so we have explored the regions affected by the two greatest acknowledged floods in the history of North America, the Great Missoula and the Great Bonneville floods. For peak, discharge, and raw stream power, these events are not likely to be surpassed. However, the effects of mega-scale catastrophic floods are by no means limited to the region directly affected by these two floods. It will be the purpose of this episode of the saga to elucidate the myriad effects of colossal floods on a variety of landscapes around the remainder of the North American continent, and to demonstrate the probability that the Missoula and Bonneville floods were actually a limited regional manifestation of a much larger event.
Wow.
So we'll skip the glossary now. But this is a good place to help get your thinking kind of in some kind of a defined order. The two major categories are erosional and depositional, right? And we can go through like erosional. We'll have scabland, butte and basin topography. Depositional will be large gravel beds and bars, right? That's deposition. Deposition always implies that it was preceded by erosion somewhere upstream. Erosional would be shear-walled canyons and gorges. Depositional, boulder streams and block fields. And I'll show you some pictures of boulder streams and block fields coming up. Erosional, oversized stream and river channels. Depositional, large erratic boulders. Erosional, coulees and spillways. Grand Coulee is an example of a majestic, gigantic coulee, but there's hundreds and hundreds of them. They're just not quite as grand. And spillways, we saw some examples. We'll be seeing lots more. Depositional, alluvial and debris fans. Erosional, strand lines and shorelines on the shorelines on the mountainsides. Depositional, fossil lake beds. Erosional, dry cataracts. Depositional, although this isn't technically correct because giant current ripples are actually kind of both erosional and depositional. Erosional, buttes, pinnacles, and pedestal rocks. Depositional, imbrication, and I'm going to show you an example of imbrication. Erosional, potholes, and then things that are likely the combination. And notice the first thing I've got is drumlins.
Yeah.
Eskers, tunnel valleys, terraces, and benches. Okay. So this shows the maximum extent of Wisconsin glaciation at this particular time. This is, let's see, this is Lake Agassiz here. And you can see that Lake Agassiz is bigger than Hudson Bay. Lake Agassiz is so big that if you were going to sail across it, you could be lost for days and see no coastline at all. And then you can see how the ice related to the Great Lakes, because you better believe the Great Lakes factor into this whole scenario. And here, colossal four-set gravel deposits in the Fraser River Valley in British Columbia, Canada. This is evidence for giant flood flows from the melting Cordilleran ice sheet. The glaciofluvial, meaning both glaciers and flowing water, this glaciofluvial flooding did not contribute to the formation of the channel scabland of eastern Washington. Instead, it discharged into the Strait of Georgia at Vancouver, British Columbia. And here you can see the tilting down of these sediments shows the direction of water flow from right to left. And this is up near Prince George.
Okay. Yeah.
And of course, you've seen this. We've been through this. Let's just keep moving, right? Then we get to this. Glacial lake spillway incision and deposition of a coarse-grained fan near Watrous, Saskatchewan. Canadian Journal of Earth Sciences, published in 1994. And this is what they're talking about across the prairie region, right? The legacy of catastrophic drainages of proglacial lakes is a characteristic suite of erosional and depositional features. Spillways generally lack deposits from the flood themselves because of the intense erosion that accompanied lake drainage. The size and morphology of these channels are the best indication of magnitude and duration of these events. The morphology of the Watrous spillway is similar to many proglacial lake spillways in the mid-continent prairies of Canada and the United States. These channels were rapidly incised by erosive flows of high discharge. Not normal glacial melting, but rapid incision by erosive flows of high discharge. Despite the problems of quantifying the characteristics of glacial lake outbursts, the channels and deposits themselves provide confirmation of the impressive magnitude of these events. Now, these impressive events that he's talking about here, that they're talking about here, they occur across the entire Midwestern prairies. All the way from the Rocky Mountain front there by Milk River and where those giant current ripples are, all the way over to the Great Lakes. And this is now from a previous Mark Lord, Alan Kehew, Sedimentology and Paleo-Hydrology of Glacial Lake Outburst Floods in southeastern Saskatchewan and northwestern North Dakota. Glacial lake outbursts occurred in the northern Great Plains as ice marginal lakes suddenly drained, forming an interconnected system of glacial lake spillways. The outbursts were highly erosive. Interconnected spillways of these large magnitude, highly erosive floods, forming an interconnected network across the whole mid-continental region. And who's aware of it? Well, just a few specialized geologists. In fact, look, this was published in 1987. This has been largely forgotten. But they're still there. The Manitou Fan, a giant boulder bar in Saskatchewan, left over from catastrophic meltwater floods circa 12,000 years before present. So these are fossil features on the landscape that you learn to recognize. Now, these boulders obviously aren't on the scale of some of the ones we've seen. However, since the deposition of this boulder bar, no force of nature has been really enough to destroy them or significantly modify them. They're basically in the same shape as when this boulder bar was built 12, 13, 14,000 years ago by these high discharge meltwater floods. And so this is more evidence. You can see these kinds of things sinuous around on the prairies, these boulder bars. A section of, we didn't even look at this one yet. This is the Livingstone Lake Drumlin field.
Oh, wow.
And look at this flow direction. You can tell the flow direction. There's a Google Earth oblique view of the Drumlin field. And there's an aerial view of a forested drumlin in Saskatchewan. Now, this is roughly the size of a lot of these drumlins. This is kind of what they look like. You can see it's forested. Now, the reason this one stands out so clearly is because it's in the lake. But if you were to drain the lake and look at this, you can see there's another drumlin form right here. The picture, high quality, there's probably another one right here. The quality of the picture isn't that great. But you can see how, you've got thousands of square miles of drumlins, and they're hidden under the forests.
Mm-hmm.
So people just don't know what's there. But now we do. We're finding out. So subglacial sheet floods were proposed on the basis of landform evidence in the Livingstone Lake drumlin field to northern Saskatchewan. Such floods required the release of enormous volumes of stored water, and it is important to demonstrate that such large storage and subsequent catastrophic releases are feasible. Some Laurentide subglacial sheet floods were at least several hundred kilometers wide and tens of meters deep. Tens of meters. Well, you're probably talking at least 30 to 50 feet, maybe deeper, but 100 kilometers, that's 60 feet wide. Mm-hmm. So what's being described here is a flow of water. It could be, tens of meters deep, could be 50, could be 100 feet deep, 60 miles wide, flowing rapidly under the ice sheet. Mean velocities at maximum discharge are estimated to have been at least 5 meters per second. Instantaneous discharges in excess of 1 million cubic meters per second, and total flow volume of about 8.4 times 10 to the fourth cubic kilometers. That's 84,000 cubic kilometers of water that into totality sculpted this particular drumlin swarm. Now change that to miles. What is it, about 4? So 84,000, 5, somewhere in that range. Let's say divide by 4. Yeah, it's going to be like 20,000 cubic miles of water. Now what's interesting about that is because one complete filling of Lake Missoula is about 600 cubic miles. So I divide 21,000 by 600, and this is the equivalent of 34 Lake Missoulas flowing under the ice sheet.
Oh my God.
Now, how come this kind of information is not more widely known?
Why do you think?
Well, I think two things. I think the scale of it is such that, it's the way science is oriented. I mean, you've got all these geologists working on this, but they're all looking at just one part of the elephant.
Yeah, here's my box. This will be your box.
Yeah,
Our boxes don't touch.
You remember the allegory of was it 5 blind men? And they were bringing an elephant into the village, and the blind men had never seen an elephant, so they wanted to know what. So somebody brings the 5 blind men or 5 blind brothers or whatever they were out to try to get a sense of what this elephant is. So one of them goes up and feels its leg and says something, like it's like a pillar, like a tree. Somebody else goes up and feels its trunk, says, it's like a big serpent, it's like a snake. Somebody else goes up and feels the elephant's ear and says, it's like it's like a big such and such leaf or something. Somebody else goes up and grabs the elephant's tail, whatever that, and somebody else feels the elephant's side. So they all have this different interpretation of what it is, but of course it's all one elephant, right? Well, it's kind of like that, It's and it goes on to say here that this 8.4 times 10 to the fourth cubic kilometers, 84,000 cubic kilometers, let's say 20,000 cubic miles, are conservative estimates for the Livingstone Lake event. And of course, it goes without saying that flows of this magnitude must have had dramatic effects all along the flood route. Of course they did. There are widely divergent theories on the formative processes of giant flutings and drumlins. If the drumlins get long enough and skinny enough, they're called flutings. But there seems to be no clear line of demarcation between what is called a classical drumlin and a fluting, which is a much longer, almost tail-like. But there's enough intermediate forms to see that they're ultimately created by the similar process. Early work in western North Carolina invoked variations of direct ice erosion and or deposition as explanations, right? Numerous researchers continue to support these explanations despite recent work in northern Saskatchewan, Ontario, Quebec, and the Northwest Territories. This work has shown that enormous, turbulent, subglacial water flows better account for a variety of erosional bed forms, including giant flutings, ice cavity-filled depositional forms, and some types of drumlins. But mainstream geology has been very, very reluctant to go there. Why? Because the magnitude of these things are so gigantic, so awesome, so beyond the scale of things that most and rates of change that most geologists think in, that it's difficult, I think. And so let's see here.
Okay, so we're seeing evidence of this all across North America.
Yeah.
And
here's a beautiful example of an underfit river from the ground.
yeah.
I'm standing up on the rim of the ancient river that was part of the same water flow that put Okotoks where it is, right? And it carved out on its way to the ocean, seeking the path of least resistance, led it through what is now the Missouri River Valley, ultimate to join forces with the Mississippi at St. Louis. But here you can see the modern Missouri is flowing. It's a perfect example of underfit. You see the ancient channel, the meltwater channel, and then, of course, the modern rivers that occupy these gigantic fluvial channels. Well, they're stuck there. They ain't going nowhere. Not unless you get, however much this flow was, 50 to 100 million cubic feet per second is probably realistic. You would have to get a flow of that magnitude to spill over the banks of this. They would then have to cut a new channel to another channel, another outlet. But yeah, nothing like that's going to happen in the near future. So the Missouri River, all of the rivers that we see are underfit rivers, they're stuck in those channels. They're not going to suddenly leap up out of their modern channel up and
Choose
go
a
over
different one, right?
Right. And here you can really begin to see the magnitude of some of those mid-continental flows. You see what you're looking at? Here's Lake Superior over here. And then you can see the flows coming down this way. These are dozens of miles wide. Each of these this is about 20 miles at least across these. You can see the flow separated right here, flowing south. This is again headed for the Gulf of Mexico. But this is coming right from the north. Down you can see these were temporary isolated islands. But the thing is that you have to realize is that these are remnants of the pre-flood landscape that was originally part of this until this downcutting occurred. This was a single landscape across here. And then we come to Lake Superior and we look at the bathymetric map of Lake Superior and we see gigantic channel scablands forms on the bottom of the lake. And we can keep going here. So this is streamlined megaflood features at the junction. This is on Mars. And your flow is from left to right. Right, you can see the tapered here. Right. And then we have
that last picture you showed is on Mars?
Yes. Yeah. So we'll at some point want to talk about megafloods on Mars.
Yes, we will. Okay, well, I won't derail us there, but
right, we don't want to. We're not going to jump that quick over to Mars.
That's why I was surprised. You just dropped a picture of Mars on me. Different evidence.
We'll skip through some of this. Let's see.
This kind of takes us back to what we said at the beginning of this podcast, where we talked about shotguns and snipers, let's say, versus a 45 caliber or 50 caliber bullet. And it's, if I'm understanding what I'm looking at better, then we're starting to see across the northern part of North America some type of series of impacts or something just berating this, sending all of this south. To say it.
Well, not all of it went south because.
Oh, yeah, and north.
Well, we'll go up here. If I go back up to my, where was it? Where I have my map of the floods, right? You see the Mackenzie River?
Right. You're not sharing anymore, by the way.
I will, though. I will right now.
Yep. Mackenzie River.
There is in fact, there's scablands right up here, and all the features you would be looking for catastrophic flows. So you had a flow coming up this way that catastrophically discharged into the Arctic, which would have ultimately come down and flowed, headed mostly for the North Atlantic. And all of these, the Lake Agassiz superflood, it discharged subglacially towards the Hudson Bay. It discharged north this way. It discharged south through, I don't know if you can see it, but there's that great bifurcation right there. Flowed down to the Gulf of Mexico. Superior lobe, that was flowing to the Gulf of Mexico. Lake Wisconsin was to the Gulf of Mexico. I'm not showing it. I need to update this, but there was also a catastrophic flow coming up this way that carved out the St. Lawrence Seaway, and that's what this is. But I'm not showing that here. And it would have been water coming down. All of the meltwater from here, a lot of it went out this way. So it's quite an epic story, and I don't think anybody's told the whole story yet. So
we're going to keep going on it.
Well, I don't know. Do you think you can handle it? I think you can. Okay, so how much longer do we want to keep going here?
I mean, I think now is probably a good stopping point. We're 3.5 hours in. We might cut off some of the beginning, but it's over 3 hours that we've been on here.
Okay, well then let's stop here then, and we'll pick up the next episode, because we want people. We've got a little more to do up there in the Northeast that's connected with the Finger Lakes, and some more research up there. Looking into Pennsylvania at some of the pretty unusual and remarkable boulder fields that are there, and what they might result from. Then we want to take a tour of the Southern Appalachians, and I want to show people the evidence that you find all scattered through the southeastern United States. And we'll take a look at the Southwest, where it's all desert. Now the Sonoran Desert, and the other desert regions of the Southwest, looking along the Mogollon Rim and some of the erosion along there. Valles Calderas, that's what I'm trying to say. Valles Calderas. Because this is a 12 mile wide extinct volcanic crater that on a number of occasions has filled up with water and catastrophically overflowed. So we'll look at that, because Valles Calderas is definitely worth a trip. We've done a number of field trips that have taken us through Valles Calderas. It's just immediately to the west of Los Alamos, New Mexico. Like I said, you're actually going into an extinct volcano.
Wow.
So that in itself is a very interesting excursion. And then you add to that the evidence that this volcanic cone, 11 miles wide, filled up with water and catastrophically flowed down into the valley and cut large channels, incised channels into the rim of the volcano, and created gigantic boulder deposits and so on around the floor around the rim of the volcano. It's very impressive stuff. So we'll look at that. That will we'll kind of cast our net out wider. And
something like this must have global effects.
Yes,
So
of course, at some point we can talk about the evidence emerging for catastrophic floods in North Africa and Egypt. When you look at Egypt and Libya and Algeria, Morocco, that whole area up there, people don't realize that. And we'll look at that. Look at the Nile Valley. The Nile Valley is a nice flat. It's actually a canyon filled with sediment, and the modern Nile River flows on top of that sediment.
Right.
And it's such a long river and so low gradient that it's not really erosive. When it comes down, at higher velocities from the Ethiopian highlands, it's charged with sediment. But then the river slows down because it's such a low gradient from, say, roughly from Aswan up to the delta, right? So there's not much erosion going on there, and this is what the ancient Egyptians built their civilization around, was the annual flood of the Nile River and its deposition of, a new layer of topsoil, of fertile material that they would then plant their crops in, right? However, just a little, in the Nile River, the valley flows right next to the Giza Plateau,
right,
immediately to the east of the Giza Plateau. If you were to dig that sedimentary infill out, which is both material that was brought up from the south, the Ethiopian highlands and that area at the headwaters of the White Nile and the Blue Nile, and backwash marine sediments that came from the Mediterranean. But if you were to clean out that thick infill package of sediment out of the canyon, it would be deeper than the Grand Canyon. In some places, it's over 7,000 feet deep.
See, this is what you were teasing us with earlier at the beginning of the podcast when I asked you about what's underneath the pyramids potentially. So,
well, you've got a mile deep chasm just hundreds of yards from the plateau and the edge of the plateau where the pyramids are built.
this picture
Now, if you were to clean that out again, you would have this sheer-walled canyon, again, 7,000 feet deep, for crying out loud. So what kind of erosional forces were at work there? All right.
big ones.
Impressive ones, I'd say that. Let me sit up straight. As I'm going through this, I'm sinking lower and lower into my chair.
Well, that means that it's probably time for us to wrap it up.
Yeah, but I think we've covered a good bit here.
Oh my gosh, we did. Yeah, no, this was satisfying, to say the least. We've been building up this picture for a while, and I've been sitting here listening, taking notes, researching after the fact, and you gave me a little taste of the spice this time.
If we keep doing this, Becket, you need to get some kind of certificate of recognition that you've achieved some level of. See, it's one of my goals right now. Is I want to, and look, I am not a professional geologist, but I've studied geology for more than 40 years. I majored in geology in college, and I did extremely well in it. In fact, I got the highest honors of my class for whatever year I was in, and I've been out in the field with dozens of geologists. So I've had the opportunity to learn directly from geologists in the field that are studying different aspects of this, geologists that have come on my tours to get my perspective on a particular geological question, right? I have read conservatively, I don't even know, thousands of geological papers, thousands. If I sat there, if I conservatively thought one a day, that's 300 a year. So if I've done that for 10 years, that's 3,000, and I've done it for 35 to 40 years. So, yeah, I've literally read thousands of papers. I've sought out many of the key researchers that have written these papers, been out in the field with them. So I've logged up, like with Brad Young and myself, just the two of us together have logged up probably going on a couple of 100,000 miles in the field. In all of these areas that we've been looking meticulously at hundreds and hundreds of outcrops, of formations, of features, of things in the landscape, cataloging them, photographing them, videoing, drone footage, correlating with digital elevation maps, now with LiDAR, investing hundreds and hundreds and hundreds of hours in doing this. And I still get people online going, "Oh, he's not a real geologist. He's this." okay, dude, you can believe whatever you want.
We'll read the funniest ones next time. I'll give you some good comments, some humorous ones based on nothing.
But I mean, it just tells me these people have no concept. They don't even know how to think, because if they did, they're going to look and go, well, I saw one comment where he's a big phony because he never provides references. And I'm like, what are you talking about? So if you watched 10 minutes of my presentations, you would know that I constantly provide references and sources. But you haven't watched 10 minutes or 15 minutes, but you are going to come on publicly online and bloviate some opinion that has no merit to it, no basis to it at all. And what you are to me is like evidence of some kind of pandemic of idiocracy that is consuming our country right now. Because we're seeing these products of education that don't know how to critically think. So all they know is to say something, oh, he's not a geologist. Well, I mean, what is a geologist? Do you have to be paid to be a geologist? Do you have to be working for the government to be a geologist? Or do you have to be working for industry, let's say the fossil fuel industry, who are probably the two biggest employers of geologists? Do you have to be working for those organizations to be considered a geologist, right? Well, maybe, if that's your definition. But
yeah,
see,
I mean, what does it even matter?
It doesn't matter. It doesn't matter. I'm just, I guess since a lot of these clips have been going up and I've started reading them, I see a lot of that, and it's like,
don't read it too closely, Randall.
Well, there's a lot of good ones, and I go, okay, here's people that really, I think, understand what I'm trying to do here. If I get paid for doing this, fine, but I've been doing it for years and years, long before I ever got paid for doing it. In fact, I scraped money together in order to do these excursions. Yeah, exactly. Worked long weeks in my building business and saved up the money, or tutoring kids in, mathematics, whatever it might be, to raise enough money, then go on these excursions to collect this data firsthand. So, my response to this kind of idiocy is like a big fat F you, because these people that come on with this, they have not earned the right to have an opinion.
And I would even say that your response to it is what we're doing. It's going more into it. It's teaching people how to critical think. I mean, obviously you'll talk more about your vision for an education center in the future, but this goes so much more, so far beyond whatever any internet comment is about this. You're putting into effect, you're putting into a more and more organized format and farther out in the world your life's work, and you're trying to do that to help the world, from my perspective, to critically think, to see the bigger picture. So I would say that's your biggest response, because that'll be the thing that consistently makes an impact and is remembered.
Well, thank you, Becket. I was thinking about just giving up and just quitting. But now that you said that, I think I'll stay with it for a little while longer yet.
Well, then me sitting here was worth it.
Well, I just, it's very gratifying to me, because what I need, and you're not a professional geologist, but what you're getting is a concentrated dose of catastrophist geology, which is no subheading that's being taught in universities. So I've had to pretty much go and do my own work to pull all of this together. Oh. What I'd like to see is a curriculum emerge that essentially it's a whole sub-branch of geology, just like sedimentology, stratigraphy, geomorphology. You've got catastrophist geology, where you people and see the reason we don't have that is because for more than a century we were locked into this straitjacket of strict uniformitarian thinking, right? And at the very same time that catastrophism is now becoming an acceptable subject for scientific discourse, we have billions of dollars being funneled into the anthropogenic climate change narrative, which would prefer not to have people thinking about the stuff we're talking about, because the goal here is to convince people that up until the human contribution to environmental and climatic change, and believe me, all of this stuff that we're seeing here, this evidence in the landscape, in the field, is the consequence of climatic change of some kind. And without a doubt, these are climatic changes that are extreme and beyond anything that we've experienced in our modern civilization. But the idea is that the science, I think, has been proceeding absolutely by these different venues. And like I pointed out last episode, the study of the Missoula flood, that's not being bankrolled by industry or government. It's geologists who are pretty much funding their own research out of pocket.
Yeah.
And so what you got, there is room for somebody who wants to come in and dedicate themselves to trying to integrate a lot of this together. That's what I'm doing, and there's others that are doing it, and it needs to be appreciated and not denigrated, right? Because, I have no particular agenda other than getting a authentic vision of reality. What really happened? And more when you're looking at the past, you can't integrate this stuff within the current dominant models of global change. It's demanding a reconsideration and an alteration, a transformation of our thinking about the history of this planet. And, of course, the subtext is the history of our civilization on this planet. But if you've got a gigantic agenda, a powerful agenda that is looking for a specific outcome, and that outcome is that human beings, civilization is responsible for provoking this impending climate crisis, which is now being compared to one of the great 5 extinction episodes in the history of the Earth, which is completely ridiculous. And we'll devote an episode to looking at the big 5. When 3/4 to 90% of all species on Earth, terrestrial and marine, went extinct suddenly within the geological framework, right? Once you see that and get your mind wrapped around to what we're talking about in terms of those events, when we talk about and break down what's now known about the Cretaceous Tertiary event that killed the dinosaurs, you're going to go back and you go, well, yeah, of course, any comparison to say that what's going on now is equivalent to that is ridiculous. It's ludicrous, right? Because if that was happening, boom, we'd be gone in an instant. We would be gone in an instant. And we'll break it down. We'll look at what is now known about the specifics of that event at the KT boundary, or events, right? Mm-hmm. But here's what I'm getting at. The point is the whole conversation has been diverted away from natural planetary and climatic change to focus almost exclusively on human contribution. And the motive for that is that if you have a true and accurate and authentic understanding of the magnitude of these ancient changes, by contrast, you're going to see what's going on right now, and you're going to realize, well, the current changes that we're seeing are insignificant within this larger context of catastrophic natural change that's been an intrinsic part of our planet's history, and undoubtedly an intrinsic part of our own human history.
Yeah.
But we don't want to go there, see? Because there's this whole political momentum behind this other narrative that's put hundreds of billions of dollars behind the promotion of that narrative.
Yeah, and it's very strange because it's very self-absorbed. It's like making everything human-centric. It's like, okay, well, the reason why all these things happen, which is kind of a strange way of creating a disconnect between finding more and more fulfillment, finding more and more meaning beyond ourselves. So
there's a word for what you just said, anthropocentric. You can add that to your vocab.
Anthropocentric.
Somebody, how are you doing today, Becket? Oh, I'm feeling a little anthropocentric. Right.
Now, coffee, please.
Okay, well, that's probably, after that rant, it's probably a good time to pull the plug on this tonight. It's getting really late here where I'm at, and I've still got things to do.
Yeah, so I'll just say this one thing, because after that rant, I think it's important to highlight that we just started the membership part of YouTube, and you guys probably see ads on these videos and stuff as well. Okay, what are we trying to do with the membership part of this? Why are we monetizing this? Exactly for what Randall just said. We're trying to fund this research. We're trying to be able to make this not just about, I mean, Randall doesn't want it to just be about him. He wants it to be about more and more people, to have students, to have other professors, to have other people teaching these things. So what we're doing with membership is you can join, it's like $2 a month or something like that. And it's for the community members who also want to vote. We're going to have members only polls where you can say, hey, I like this. I want to hear about this. You're going to have member only chat, where essentially we're trying to insulate a community of people who are willing to spend $2 to at least be good actors who are trying to contribute to this. And also the funds help.
Well, that'd be awesome because, you know, even before, when I was funding it on myself, that was my priority, was getting out there, doing the research and sharing the research. So if I have more resources to do that, I will be doing more research because, look, I now know that there's a lot of young, recently graduated geologists and in related disciplines that are coming up and that are more open-minded than some of their elders that are still locked into the uniformitarian paradigm and who have mastery of a lot of the new technologies and stuff. Yeah, to bring some of those in and literally create a discipline that a geological discipline whose focus is on catastrophism. And it would tie in with catastrophic climate change, the mass extinctions, all of these things that I think are interrelated. Impact geology, all of that. And it needs to be a grand synthesis of these things that we now know about the way our planet changes.
Yeah, and it ties into even more than that, even more than geology. It ties into all these different ideas. And I mean, a good example of young people who are doing this too is at the Cosmic Summit. Like, you have people that are content creators and also young academics who are coming together to explore these heterodoxical ideas and do it responsibly, not just come here and say something. So it's a good venue for that as well. You can look to people who are speaking there to at least start that research, but we want to build that community more and more and more.
And what I like about the Cosmic Summit is George isn't really reluctant to say, yeah, we're bringing a spectrum of viewpoints and perspectives together here. It's not going to be limited to only a narrow range, dry, specific discipline, and anything outside that has no place, or, you know, a very narrow interpretation of what's possible within the whole realm of nature. Hearkening back to the famous paper by William R. Davis, the founding father of geomorphology, called The Value of Outrageous Hypotheses. And in there he excoriates his colleagues for just getting too dogmatic about what's possible and what's not possible. And he cites this whole litany of things that were considered impossible that had become reality. And we need more of that. We need more because there are people out there that think, that's fringe. They're too ready and willing to sling the label pseudoscience. And the thing of it is they, in the big picture, if they're developing models of reality that has no cognizance of any of the things that we've been talking about, how valid are those models? Yeah, I think that's a fair question.
It's a very fair question. And I think pseudoscience, when it was said integrally, used to be because they were pointing at people being lazy, and now it's kind of flipped too.
Yeah, accusations of pseudoscience flow both ways.
Yeah. Yep.
So I try to stick to what's known. I do believe in Carl Sagan's famous saying that extraordinary claims require extraordinary proofs. Yeah. My approach, that some people don't like, because some people just want the answers without having to do the hard work. They just want to be spoon-fed. well, what's this? What happened? What do you just tell me what? Well, what I'm going to do here is I am laying out the case, and I want you to exercise your own faculties of reason and see what you conclude from the evidence that I'm going to show you. And I'm very interested to see if you, after due consideration, arrive to some of the conclusions that I've arrived. But I'm not going to sit here and spoon feed you all of the interpretations. I want you to engage and do some positive thinking yourself. And I've found way too many people want to sit back and just be spoon-fed. They want to be entertained, but they don't want to be educated in the process. And we're going to change that. We want to try to make education very entertaining. And to me, learning this stuff that we're talking about here and then being able to go out in the field and experience it firsthand, that's very entertaining to me.
How much better does it get? You're able to truly pursue truth.
Sure, that's it. So the bottom line is, I think we can say with confidence that there's one hell of a big epic story that's been waiting for us. And the time is right now to disclose, to peel back the layers and disclose this story that's been writ so large into the surface of our planet that we haven't been able to see it because we're microbes within this larger stage. And now we're expanding our vision. Technologically, we're getting eyes and insights that we didn't have a few generations ago. We're doing what we have the potential to do now was impossible for our predecessors of a few generations ago. They didn't have the tools, they didn't have the expanded vision and the critical understanding to begin to discern this story that's been waiting for the human species to evolve to the ability to begin to read it and decipher it. And I think that's where we're at now. I think we're at the point where, we can see. And, we're going to be tying together, just like we're tying together the events over North America. We're going to, I think, come to the conclusion that we're looking at, the global events. And then to understand those global events, we have to not confine our thinking to purely terrestrial domain. We have to expand our thinking into the cosmos. And then we will have a framework for understanding what's ultimately driving these things, these events whose aftermath we're seeing preserved in the landscapes of the earth.
Amen. Amen, brother. All right. Until next time. Thank you,
right.
Randall.
Adios.
Adios.